Shemaiah. But I would like you all to think about what you think these answers are, either technically or off your top of your head, like your gut feeling. So if you have a single dice, by the way, you all know what a die is. You know, it's a little six-sided cube. It's got numbers 1, 2, 3, 4, 5, 6. First of all, if you only have one of them, what's it called? It's a die. D-I-E. But I felt weird writing that because I don't know, I just call it a dice anyway. But technically, if you have a single die, what is the probability of rolling a 5, an even number, a composite number, or a 7?
Is it redundant to say single die?
Probably. Yeah, if you have a die. But again, that sounds weird. So think about those, what you think the probability is. And then if you have a pair of dice, and that's really dice, what is the probability of rolling a pair of 6s, both odd numbers, a sum of 2, a sum of 7? And finally, how many ways can you flip a coin 3 times? So just kind of consider those questions for a moment. Maybe just to yourselves, I don't know. Or discuss it.
Okay, how many times are you rolling it?
Just once. Very good question. You only roll the dice once.
Oh, it's 6-sided. 1 out of 6, exactly. It's 6-sided. An even number. Son 5, sería 1 out of 6. 3 out of 6. 1 out of 3. Is a composite? What is a composite?
We only have one.
Odd? Isn't that an odd number?
Yeah. Okay, do you roll dice? How you're rolling? 7.
It's not one.
1.
7 is igual. Ah, 0. Pero chiflada, te digo.
Trick question.
Seriously. ¿Qué es un composite? Bueno, regresamos a eso. Ahora, if you have a pair of dice. A pair of 6 sería igual a 1 de 12. No. 1 de 6.
Sí.
Porque por eso nomás hay un 6 en uno y un 6 en el otro.
Sum of 2.
Like what, 1 in 100? Sí, entonces. No, pero ahí cambia. Ahí serían 2 y 3. Porque tienes. Porque para la otra. Ah, no. No.
2 de 12.
No sé.
No.
No, para primero digo que si es 1 de 6, porque entonces tiene que ser un par. De 6. La diferencia con la segunda parte es que no tiene que ser el mismo número. Puede ser un 3 y un 1. Tú tienes el 1, el 3, el 5, el 7. Pero, no, porque mira, tienes el 1, el 3, el 5 y el 7. Y luego con el 1 te puede salir el 3 o el 5. Y luego con el 3 te puede salir el 1 y el 5. Y luego con este. All right. What do you think, folks? Should we discuss these?
Yep.
Let's try the first one. What's the probability of rolling a 5? What happened? We're just going to go through it. However you want to answer it. It can be technical. It can be from your gut. What's the probability of rolling a 5?
1 in 6.
Yeah, 1 in 6. Okay. Did anyone say anything differently? No? Okay. Then what's the probability of rolling an even number? 1 out of 3. 1 out of 3?
1 or 3 out of 6.
1 out of 6?
3 out of 6. No.
3 out of
3 out of
6?
6, but just one out of 3. If we're reducing.
Reducing.
So the number of odd numbers? No, the number of even numbers is 2, 4, and 6. That's what we have on a die. And the total number of numbers on the die is 1, 2, 3, 4, 5, 6. So what's the probability?
3 out of 6.
Yeah, 3 out of 6, which reduces to what, Lynette?
1 out of 3. 1 out of 2.
There we go.
Yeah.
That happens to us. Okay, very good. And so that one we actually demonstrated a little bit more about why that's the probability. What's the numerator?
What you want.
Yeah, what you want to happen. And the denominator?
All your options.
Yeah, all the things that could happen. Okay, so what's the probability of a composite number? We might need to remind ourselves what a composite number
Yeah,
is.
my God, I don't know what that is.
Oh, well, what's a prime number and a composite number? 1 is a unit, it's the counting unit, it's neither prime nor composite. 2 is prime, 3 is prime, 4 is composite. Why is 4 composite?
You can add two numbers.
Yeah, we not add.
Multiply.
You can multiply two numbers to get it. Okay, 5, prime or composite.
Prime.
Prime 6, prime or composite.
Composite.
Composite, because that's 3 times
2.
2. And then 7,
No.
prime 8,
Composite.
composite 4 times 2. Okay, well that's enough. So how many composite numbers are there between 1 and 6?
2.
There's 2. So the probability would be?
2.
Yeah, 2 out of 6. 2 out of 6. Or Lorena, 2 out of 6? 1 out of 3.
1 out of 3.
All right. Okay, and what's the probability of rolling a 7?
0.
Now this is how we would write that. We would say probability
No.
of rolling a 7 in this particular case. We're saying, what's the probability of rolling a 7? It's 0 out of 6, which is 0. Now, what's the probability of you rolling the dice and it landing?
Check.
Yeah, 6 out of 6, right? I mean, I guess that's not really the official way to ask that, but what's the probability? I could have said that better.
Number.
Wait, yeah, what's the probability of rolling a number? And that would be 6 out of 6. So all probabilities exist on a spectrum between what and what? What's the lowest probability and what's the highest probability?
3 and 1.
They're between 0 and 1. So we've got this nice little spectrum of probability where we have 0 on the one hand and 1 on the other hand. And what would be a word for the probability of 0?
Is that where the no one came from or not?
Hmm?
No. Nada.
Like if I told you the probability is 0, then that event is,
Not likely or not?
it's not just not likely. I mean, not likely can still happen. If the probability is 0, that event is
Not happening.
impossible.
Oh.
Yeah, it's not happening, exactly. So that's an impossible event. Whereas if the probability is 1, then how would you describe that event?
Always.
Yeah, always, it's a sure thing, right? And so probability is everything in between, you know? You either have things that are impossible or they're a sure thing, and everything else in the middle, that's the world of probability. So it could be 0.5, that's like a 50-50 chance. Or you could be somewhere up high, like 0.9. How would you describe an event whose probability is 0.9?
Very likely.
Yeah, fairly likely, right? Whereas why would you describe an event that was a 0.1? 0.1, what would you call it? Yeah, very unlikely. Or I'll just go ahead and say unlikely. Okay, so all probabilities are a decimal between 0 and 1. We'll calculate them first as fractions. Why is it that probabilities always begin as fractions? And then we just type it into a calculator and we get a decimal. But why does it start as a fraction? Because that's the definition. We have to actually count these two sets. We have to know how many items are in the numerator. We have to know how many items are in the denominator. Then we can form a fraction. Then you can type it into your calculator, and you will get a decimal that's between 0 and 1. Is it possible to calculate a probability that's more than 1? Like, say, 1.2? Could you ever get a probability that's more than 1? What would that even mean? Like you're rolling a dice, and suddenly, not only can you roll 1, 2, 3, 4, 5, and 6, you could roll a 7?
It's a sure thing.
Yeah, I mean, you're saying that there's more ways to get what you want than there are even ways to get something. So is that possible?
No.
Yeah, that's not possible. So you can't have a probability greater than 1. And can you have a probability less than 0? Could you have a negative probability?
No.
And what would that even mean? What would our numerator have to be? I mean, it's one thing for our numerator to be 0. You know, there's 0 ways for something to happen. But for the numerator to be negative, what would that even mean? That there's negative number of ways to do something? It makes no sense. All right, so we're just introducing our ideas here. What about the second question? If you have a pair of dice, what's the probability of rolling a pair of 6s? And I'll help us all out. Here's a sample space. This is called a sample space. The sample space is usually a grid or some sort of diagram that actually tells you all possibilities, all true possibilities. So how many possibilities are there when you roll a pair of dice? where one of your dice is green, one of your dice is red, and then every entry in that grid tells you one possible throw you could get.
36?
Yeah, so there's 36, right? Because you've got 6 possibilities of one dice, 6 possibilities of the other dice. So you got 36 possibilities there. So what was the probability of rolling a pair of 6s?
1 out of 36 then?
1 out of 36. Yeah, there's only one pair of, well, there's only one pair of 6s in that grid. And so it's 1 out of 36, because there's 36 ways you could roll a dice, and just one way that you could roll a pair of 6s. So that's it. It's just 1/36. What's the next question? What's the probability of both of them being odd numbers? Both of them are odd numbers. This is tricky. It would be easier if you had this and you could circle them on your own paper, right? But where are double odd numbers? Well, first of all, here are my odd numbered rows, right? 1, 3, and 5. And then here are my odd numbered columns, 1, 3, and 5. So we're looking for the intersection of those rows and columns. So, I mean, if there's 3 odd numbered rows and there's 3 odd numbered columns, how many would that make? 3 by 3? 3 times 3? 9? Would it be 9? There's 1 and 1, 3 and 1, 5 and 1, 1 and 3, 3 and 3, 5 and 3, and 1 and 5, 3 and 5, 5 and 5. Are you convinced that it's 9? Okay, so it's 9. 9 out of what? Yeah, 9 out of 36, which reduces to 1 and 4. Yeah, so the probability is 1/4 or 0.25. So you've got a 25% chance of rolling both odd numbers. And by the way, folks, probability. It could be 1 as I write a 6. Isn't that funny how the brain literally is saying the number 1 and I pick a 6? Okay, 1 and 4, or I could call it 0.25, or I could call it 25%. 45%. Which is the best way to tell your audience a probability? Yeah, I mean, I guess it really depends on your audience. Percentages are nice because most people understand that and they have a gut feeling. Like, Nick, if I tell you there's a 90% chance I'm going to give you $100 tonight, Nick could be feeling pretty good. Like 90% chance, I'll take those odds. Whereas if I tell you there's a 1% chance I'm going to take all you guys to see Star Wars tonight, you know that's not going to happen. 1%, yeah. Now, that's nice because we have a gut feeling. The 0.25 thing, I think, largely confuses people because you're like from between 0 and 1, 0.25. It's just weird that they're all decimals. But I mean, what's the difference between the decimal and the percent? You just move the decimal and you put a percent sign. So that should be no big deal. Whereas 1 and 4 is actually a really nice representation because it literally tells you something. What is it telling you?
1.
1 way out of 4. Like it's telling you about the sample space that you were talking about. Okay, what was my other question? What's the probability of both odd number? Oh, the probability of the sum of 2. So how often will the dice add up to 2? It's just once, right? The 1 and 1. And what do we call that when you gamble and you play with dice? Snake eyes.
Oh.
Exactly right. Those are snake eyes.
Don't ask me how I know.
Yeah, what do you call these when you get 2 6s?
Dominoes.
That would be nice. I think they're called boxcars. I think they're called boxcars. I don't know why. That's more obviously snake eyes to me, but whatever. Last question. What about the sum of 7? What's the probability of rolling a sum of 7?
6 and 1, 5 and 2, 3 and 7. Oh, okay. Oh,
Where are the 7s?
diagonally.
Yeah, they're on the diagonal, right? Now, did everyone just see all the 7s, how they're on the diagonal? Okay, watch. This represents the sum of what's on the dice when you roll 2. So you remember just a second ago you had all the 6 and the 1 and the 5 and the 2. So that was your diagonal representing the sum of 7. And this screen will tell you the sum of each of those. So there again was the snake eyes. 1 plus 1 is 2. And there was the boxcars. 6 plus 6 is 12. And so this is a nice little grid. What sum are you most likely to roll?
7.
Well, 7. And that's why when you play craps, what are you normally trying to roll?
7.
I think it's 7, right? I honestly have never played craps. I don't know much about it. But in the game of craps, if you roll a 7, I think you get to keep going. And then it's like all special if you get snake eyes or boxcars. Why is it special? It's the least likely thing to do. Yeah. So there's all sorts of questions and probability questions you can ask about these. Okay, and was that my last question? Yeah. Okay, now, how many ways can you flip a coin 3 times? This might be easier if we start with 2 times. So on your own paper, just anywhere on your paper, model how many ways you can flip a coin twice. And I'll start you off by saying, well, it could be heads, tails. What are all the different possibilities of flipping a coin 2 times? Just 2 times.
So before?
Yeah. But write down the actual possibilities.
Positive, positive, negative, negative.
Positive, positive, negative, negative.
And then positive, negative, and then negative, positive.
Oh yeah, now that's super fun. So Carmen just took heads and tails and turned it into pluses and minuses. And that's correct. It could be plus plus, it could be minus minus, it could be plus minus or minus plus, which is the same representation of our heads tails questions. It could be heads heads, it could be heads tails, tails heads, or tails heads. So yeah, okay, so there's 4 different ways for that to happen. What's the most likely thing to happen? To get 2 heads, 1 head and 1 tail, or 2 tails?
Head and a tail.
Yeah, right. You're actually more likely, if you flip 2 coins in a row, you would expect to get 1 of each. You'd expect that. Okay, well that was an easy one. Now do 3. How many different ways can you flip a coin 3 times?
9.
Good
Over.
guess.
6.
Another good guess. No. Now stop guessing and write it down. Yeah, folks, try it out. Put down triplets of T's and H's. And I encourage you to try to be systematic about it rather than just kind of willy-nilly, haphazardly trying different things. Try to be as systematic as possible.
Oh, 8?
Is that a guess?
Yes. No, not yet. I'm sure.
What if I told you it's wrong?
Oh, I think it's right.
You think it's right? It's wrong.
Really?
No, I'm just messing with you.
I think it's 8. Like 2
No, it's
to
8.
the third.
It's 8. How did you get 8?
2 to the third will be 8.
Right, it's 2 to the third. Yeah, so what are the possibilities? What are they actually to write them down?
Positive, 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 negative.
Oh,
negative,
yeah, there you go, yeah,
And
okay.
then just keep going.
Okay, so do you have a systematic way of writing them down? I hate to stop you before you finish. Go ahead, take another minute and finish writing down all the different possible ways. Carmen shared with the group that it's going to be 8. This is just one of them, huh? That's awesome. Oh, nice. Ah, that's a way to do it. Now, of course, if you're looking for a good time on Friday night, you can try to write down how many ways you can flip a coin 4 times, and then 5 times, and so on. Well, there are a couple different methods I saw. I think I'll share Lorena's way first because it's useful in so many ways. Everyone did this with me. You start by making a branching tree. You flip a coin once, and it's either heads or tails. Now, after that flip, let's say after the head flip, once again I flip a coin, and it's either heads or tails. And then after I flip the coin at tails, it's either heads or tails. Now, if you look at this nice little branching tree and you follow each branch, look what you get. This branch is head, head. And this branch is head, tail. And this branch
3 points?
is tail, head. Well, I'm getting it.
Gotcha, okay.
And then this branch is tail, tail. All right, so that's a really handy, helpful method because now what do I have to do
Yeah, that's it.
to get my third head? I mean my third coin. I'll just go ahead and show another branch off of each one. And each one could either be head, tail, or head, tail. And at this point, I don't even have to really write them down, do I? I mean, you could just follow along. Head, 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 tail, head, tail, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. So that's a really nice specific algorithm for getting all of them. Another one, though, that I saw, that I think I saw some of you using, was you can start with all heads. And then just introduce one tail. If you just have one tail, it can either go there, there, or there. Right? And then the rest would be heads. Okay, you could have 2 tails. What if you have 2 tails? It could be there and there, it could be there and there, or it could be there and there. Is there any other possibility for 2 tails? That's it. Okay, so that was 2 tails. So then I could have 3 tails, and that's it. The nice thing about these two methods right here is that they're systematic. They're systematic. You know you're going to get them all. Also, take a look at this method. This one had how many heads? Or I should say how many tails? None of them. This one had how many tails? 1. And this one had how many tails? 2. And this one had how many tails? All 3. So this systematic method also kind of groups them together. So you know what you're looking at. So now I could go ahead and ask all of you, what's the probability that I get 2 tails if I roll? I mean, flip a coin 3 times.
3 out of.
What's the probability of getting 2 tails? 2 out of 8. So 2 out of 8. The probability of getting 2 tails is 2 out of 8. What's the probability of getting 3 tails?
1 out of 8.
1 out of 8. Yeah, sorry, the 3 there means how many tails there were, but what's the probability of getting 3 tails? 1 possibility out of all 8. And what's the probability of getting all heads?
1.
1 possibility out of all 8. So all of these represent sample spaces, okay? The picture that I had up there on the board, that's a sample space. This picture of all the heads and tails, that's a sample space. Even this tree diagram, that's a sample space. And the benefit of a sample space is our brains were not meant to think about these things all by itself. You're not supposed to just shut your eyes or look at the ceiling and try to think about all these possibilities because our brain is woefully inadequate for the task. So you make a diagram and you write it down. That way you can just look at it. By the way, what if you did want to take the sample space? Are you all ready for this? You have to watch. You're going to love it. What if you want to take the sample space for 2 coins, and then write down the sample space for 3 coins? How could I take this and do that? Everybody ready? You're going to really love it. That's 2 coins in a row, right? Either it's preceded by tails, or actually maybe the tails. Maybe the tails could go at the end too. Shoot, I was going to say, no. I think I'm doing that wrong. Yeah, I think I'm doing that wrong. I could either put tails there, and then that would be one possibility, and then I erase it, and I put heads there, and then that's the other possibility. Do you think that covers all the possibilities? If you either precede everything by an H, or precede everything by a tail. Yeah, that covers it. All right, well this has been nice. These are just some fun introductory ideas that are in this chapter, where largely the chapter culminates by calculating probabilities. We're calculating probabilities. In order to calculate a probability, what do you have to be able to do? Count things, right? That's the precursor skill. You have to be able to count what's in a given set, and then from all that counting, then it's just a matter of just saying, oh, those are the ones I want, that's the total, and then that's it, that's probability. So what definition of probability will we say is our shorthand? Well, at least this is how I always do it. 1 out of total. That's the definition of probability I've been using my whole life. So especially when you roll 2 dice, you say, what's the probability of rolling 2 numbers that are right next to each other? It's like a 2 and a 3, or a 3 and a 4, or 4 and a 5. You just go through and count all of those, and then that's your probability. What you want it to happen out of 36, which is the total. All right. Well, folks, that was just a dandy little warm-up. By the way, do any of you play cards?
Poker
Have you
card?
seen a deck of cards?
Or what?
What's that? What's that, Carmen?
I just said, is it poker card?
Yeah, poker cards. Yeah, that's a full deck of cards. Does that look like a full deck of cards to you?
52 on one?
Yeah, there's 52 cards. Well, some of the problems in this chapter will be about cards. How many different suits are there?
4.
4 suits, right? Heart, diamond, black, and spade, club. And how many different colors are there? 2. And how many different numbers are there?
Numbers or
13.
Well, you know, the variety, 13.
Oh, okay.
But you're right, how many face cards are there?
Oh, that is. What's
How many
Four.
face cards are there?
Oh.
Oh,
Just the Jack, Queen, King, right?
12.
The ace doesn't
Yeah.
count as one?
Well, does the ace have a face on it?
No.
I know ace rhymes with face. Yeah. What's that, Nick? Oh, okay, well, I'll let jokes. Yeah, so ace is not a face card, just Jack, Queen, King. So there are 3 face cards and 10 number cards, which makes sense. 10 plus 3 is the 13 total. How many cards are there in a deck? 52.
I thought it's 54.
54 with the 2 jokers.
Oh.
Yeah. Okay, so we will use cards as well tonight as one of our sample spaces. Why do you think they call it a sample space?
Different possibilities?
It's called the sample space, I suppose, because from that space of possibilities, you can choose your sample of what you want. You can take a sample. You can reach in, take a sample of them, and that would be your probability. All right, today is excitement. Where are we? February 14th?
No school.
No school on Monday. Yeah, no school on Monday. Although, didn't we talk about having a bonus class?
Yeah.
No.
We were just
Oh,
going to come
no,
in
we
anyway.
didn't talk about that.
Shemaya, you were the first person to vote. You said you wanted it.
Oh, no.
Okay.
Not that.
So, yeah, folks, chapter 7 is pretty exciting. We're in the home stretch. Can you believe this class is already almost over? So we'll do chapter 7, 8, 9, and then we will review and take the third test, and then we'll have a whole class session just to review for the final exam, and then we'll take the final exam. I know, it's pretty wild.
Wow.
Now, I should have a joke for you guys. That's pretty. Are you depressed? Look down there. There's no jokes.
No Valentine joke, no nothing.
Yeah, no, I have a joke for you. What joke? No, I have a joke. Okay, here it is. You ready? I have to remember what my joke was. I just told it in my other 2 classes. You already heard the. Oh, why is the math book so unhappy? Because he had so many problems. Yeah. That's it. Okie doke. So, chapter 7, sets and probability. Again, probability is the culminating idea. That's what chapters 7.3, 4, and 5 are about, and 6. But the first couple, chapter 7.1 and 7.2, are about sets. Now, why do you suppose we're interested in sets? And by the way, what is a set? A set is normally written as curly brackets, and then you put something inside the set. Like, that's the set of even numbers on a die. On a die. On a die. So set theory is going to help us count things, because you can't calculate probability correctly unless you know how to count. So here we go. We're starting off in chapter 7. Did everyone get a chapter 7 packet? And everybody took some candy? Care of Lorena? Boy, Lorena, sometimes I can flip that R and sometimes I can't. I feel like I should just give up.
Okay. You can practice.
I won't give up. I'll just keep practicing. So, I have some notes for you. They're just going to go up at the top there. Set theory notation. So first of all, let's just go ahead and say that we define the set P to be the numbers 2, 3, 5, and 7. Any wild guesses on why I called that set P?
Prime.
Because they're all prime. Those are your prime numbers less than 10. Are there any other prime numbers less than 10? That's all of them. 1 is the unit. It doesn't count as prime or composite. And the other numbers, 4, 6, 8, 9, 10, those are all composite. So once you define a set with curly brackets, you want to say if something is in the set or isn't in the set. So we have a special membership notation. So we would say, like here, we'd say 2 is a member of the set P. Now that little symbol that I just drew, it's on your paper if you just scroll down and look at number 7. I'm sorry, number 1. Do you see the symbol? Try to make your symbol look like that. It's basically just a curve, like a sideways parabola with a line through it. It looks like an E, but it is not an E. Yeah, good. It looks like a C with a line through it. So this says 2 is a member of set P. Or if something's not a member of a set, like the number 4, I could say 4 is not a member of set P. And you just draw a line through it. So that's how to define a set, and that's how to talk about membership in a set. Okay, you can also define a set using words. You can say P is the set of all numbers such that, and that line right there means such that. So it's a number such that X is a prime number less than 10. And that would be acceptable. That way, you know, just in case the set is really, really big, you might not want to sit there and list them all out. I mean, look how easily right now I can change my definition of P to all the primes less than 100. And I don't have to list them. I can just go ahead and say all the primes less than 100. And you're just
Here we're saying X is
all of the numbers X such that,
okay.
now line there reads such that. All numbers X such that X is a prime number less than 100. Or 10. So to stick with the letter P, I should keep that as a 10. Okay, so those are some set theory basics. Let's say that we have a couple of other sets. We're going to define the set A as just the numbers 2 and 3. And we'll define the set B as just the numbers 3 and 6. I'm no longer claiming that these are prime numbers or anything. I'm just telling you A is the set that contains the numbers 2 and 3. B is the set of numbers that contains 3 and 6. I'm not saying anything fancy about it. Like I'm not giving the definition of them. Okay, well, so other than talking about membership, and I should write that word there, membership, that's how you say that a set is an element is a member of a set. So that's membership. You might want to talk about whether or not a set is a subset of another set. What do I mean by subset? Yeah, inside the other one. It's a smaller collection of elements, meaning if I took the set P and just deleted a few elements, I would have set A. So I say A is a subset of P, and I write it like this. A is a subset of P. And in that case, again, you can look at that symbol down there right above number 4. It's kind of like the same curvy C, but the line goes underneath it. And now that reads, A is a subset of P. To be a subset, it means if I went up to set P and all I did was cross out elements, I would be able to create set A just by deleting. So subset by deletion. So what would I say about B then? Set B. Is B a subset of P? It is not a subset of P. So again, you put a little diagonal line through it, just like you did with the membership symbol. So 4 was not a member of set P, you put a line, a slash through it. And here B is not a subset of P, you put a slash through it. It doesn't matter that set B has the number 3 and so does P. The point is that B also has this element 6, and that makes B not a proper subset of B. Because I can't get set B just by deleting things from P. Okay. Have you ever seen or worked with this notation before? Yeah? Okay, so maybe you have. You know, maybe in a prior math class, at some point you did. The key symbols that we've seen so far, if we wanted to try to keep track of them all, we've got set brackets, we've got membership of, and we've got subset. So those are our 3 symbols so far that we've talked about. Just the bare fact of making a set, being an element of a set, or a set being a subset of another set. Okay, there's a few more definitions that we need. One is called union. Now, we've already dealt with union before. When did we deal with union before? Yeah, intervals. So let's say I wanted the intervals of, let's say here 0, positive infinity, and negative infinity, but not including 0. So that would be the interval negative infinity to 0, or 0 to infinity. What does that U stand for? Union. It means or. So you can choose anything from those 2 intervals, and it would be an acceptable answer. Union means or. So union means or. Union also means either, if that's what you prefer. Meaning it can come from either of those sets, and that's okay. Yeah, either or both. The key word is either, because both means something else. And in specific, Lorena, is there an element that is in both of these? No, not technically. There's no overlap there. So we want to focus on the word or either. So what would the union of A, union B be?
3.
So A union B is the set that has any elements that's in either A or B.
2, 3, 6.
Yeah, 2, 3, 6. Like a marriage, right? Once you're married, everything is common property. If it belonged to either of you in the beginning, now it belongs to both of you. It's part of your merged either or set. So that's a union, unless you have your prenup. But isn't the prenup just to protect your stuff if the other person dies or divorces or something like that? I don't know. Okay, so that's what union means, and union is a U. Intersection means both. So where do they intersect? What do they have in common? In common would be another good word, in common. So what would A intersect be? And by the way, intersect is an upside down U. Right? So U is probably from the word union, so they just kept that and then they just flipped it upside down and called that the intersection. So what do A and B have in common?
3.
Yeah, just the number 3. So A intersect B is just the number 3. All right. Questions about our notation so far? Okay.
Can you repeat for 4, between 4 and P, that one again?
4 is not an element of P.
Okay.
Yeah.
So can be any number between, like, for example, like 8 can be like that.
8 is not in P either. Only these numbers are in P. Only the numbers I expressly state.
So for there, can I put 8?
Oh yeah, you could say 8 is not in P. You could say banana is not in P. Right? I mean, I could say Carmen is not in P. Yeah, anything that's not in there is not in there. Yeah, really good question.
Thank you.
Sure. All right, folks, go ahead and try the first few questions. You can go ahead and do the whole first page, as a matter of fact. Go ahead and do the whole first page. Well, at least do 1 through 5.
That's true or false?
Yeah, tell whether the statement is true or false. Should we just do these as a group, or do you just want to try them out? Yeah, let's try number 1. Is 7 a member of that set? No. So that's false. That's a false statement to say that 7 is a member of that set. Yeah, 7 is not inside it. Yeah. What about 3? Is it true that 3 is not a member of that set? Yeah, that's true. It's true that 3 is not a member of that set. What about number 3? X, this is the set of all numbers X such that X is an even counting number between 8 and 14.
False.
And is that set just the numbers 8 and 14?
No, false.
No. What number should be in that set?
10 and 12.
Yeah, 8, 10, 12, 14. So that's false.
Wait,
Number 3?
Yeah.
Yeah, no, it's okay. First of all, let's just agree. If X is an even counting number between 8 and 14, just tell me what those numbers are. 8? There you go. And they said it's just 8 and 14.
Oh.
So that's false. They didn't include them all. Good question. And then how about number 4? Is that first set a subset of the second set, or is it not? Yeah. And remember, subset means the process of deletion. So can I get the set 5, 7, 9 from this set just by crossing out members? Yeah, I just cross out the 4 and the 6, and therefore it is a subset. What about number 5? Is this set a subset of the latter? No. No, because to be a subset, first of all, you got to have fewer elements or equal, right? You could have the same elements, you'd be a subset, but you have to have fewer elements to be a subset. So that's already false just by not even really looking at anything. It's just false. Okay, now this is where it gets to be fun. Now they have some actual problems for us to do. So take a look. I mean, you might want to write it down again yourself. Yeah, I think you should. So let's write it down again ourselves. It says, is C a subset of D? So is C a subset of D? What we're going to do is write out subset C. I'm sorry, C. That's just 5 and 8. And then is that a subset of D, which is 2, 5, and 8? So is that true?
Mm-hmm.
Yeah. Yeah, all you have to do is delete the 2, and therefore it is a subset. Is it true that C is not a subset of B? So let's see, C, not a subset of B. So C is 5 and 8, and B is 5, 6, 7, 8. So is that true? Yeah, that's false. 5, 8 is a subset of 5, 6, 7, 8. All I'd have to do is cross out the 6 and the 7, and then I'd have 5, 8. So that statement is false. All right. Take a look at 8, 9, 10. They have some intersection and union. There's a symbol up there I haven't defined yet in number 10. So let's do 8 and 9 first. What's the intersection of 3, 6, 9, 12, and 3, 9? What do they have in common? They're just 3 and 9, right? So the intersection should be 3, 9. But they listed all sorts of other elements, so that's false. Write down what the correct intersection would be. The correct intersection would just be 3, 9. What about number 9? Write out the correct union. Write out correctly what elements is in either of them.
Oh, union.
Yeah, this one's union. So what is the correct union? Yeah, 6, 12, 18, 24. So that statement was actually true. The union of those sets is what they said it was. Now, in this next one, number 10, they have a symbol that we did not define yet. What is that symbol? What does it look like anyway? Yeah, circle with a line through it. Very important, that circle with a line through it. The line should be a diagonal. It is not a line straight up and down. That's the letter phi. And it's not a line with a letter going sideways, because I don't know what that is. It's a line, it's a circle with a line going sideways, and it means the empty set.
What is
That's
the
the
empty
empty
set?
set. Well, yeah, what is the empty set? The empty set is like the never-ending story when the nothing came to destroy Narnia. Narnia? Wrong story. Anyway, what's inside the empty set?
Nothing.
Nothing. The empty set is literally a pair of curly brackets with nothing in it. Is that not depressing and strange?
Why? Why do we need it?
Why do we need it? Well, to be able to answer questions using symbols only. So for instance, well, I don't have a for instance right there. Let's say I did the intersection, here, let's do this one. I'm going to intersect just the set with the number 1 and the set with the number 2. So what do they have in common? Nothing. So rather than saying the word nothing, I want to be able to provide I want to deal with sets only, right? If I start with sets, I want to end with sets. I want to be in the language of sets. So we create up this new set called the empty set, we call it that. That way you can still answer problems using set notation, instead of using the word nothing. Okay, so they're saying, what does the set 13, 2, and 9 have in common with the set empty set? Nothing. So this should read 13, 2, 9 intersect empty set equals empty set. Right? That should be the empty set. They have nothing in common. So that's false, yeah.
So if it was a union,
If it was a union,
then we would have brackets, the empty set notation, the 2, the 9, and the 13?
yeah, if it was a union, then it would be either, yeah, it'd be anything. It'd be fine.
It would be anything including nothing.
Yep.
And then
Now what's really weird is that sometimes people want a set with the empty set in it. Like look at this. This set will blow your mind a little bit. I want the set Q to be the set of all symbols used in set theory. Right? Okay. So it's a set of the symbols used in set theory. And so in this case, watch this one, the empty set is an element, is an element of Q. Right? The empty set is actually an element of Q because
it's part of it.
it's in there. So it's just a symbol and you can use it for things. All right. Well, let's take a look at a little bit more notation. There's a lot of new vocabulary and terminology, so we're just layering it in as we go. Moving on. Whoa, look how big those sets are. U, A, B, and C. Which set is the biggest? U. Take a look at A, B, and C. Are the elements of sets A, B, and C all contained within U? Is there any element of A, B, or C that's not in U? Yeah, so it's all in there. Okay, so now in this particular situation, oh, I need to keep up with all my symbols here. So I have union, intersection. In this case, U now, this is capital U. It's no longer the union U. U represents the universe. So within set theory, every once in a while, we want to limit ourselves to a particular universe of symbols. And so we're saying, for the following problems, let's consider the universe to be this set U. Q, R, S, T, U, V, W, X, Y, Z. Those are the only elements that we are going to consider. The universe is constrained to that, and therefore, set A, B, and C are each subsets of the universe. So that U stands for universe. The universe is always relative. You're just saying, this is the most symbols I'm going to deal with right now. And let's do problems within that universe. So I'm going to start by writing out my universe, which was just the letters Q through Z. So Q, R, S, T, U, V, W, X, Y, Z. And I won't write down all the other sets just yet. But let's take a look at number 11. 11 is asking us to write down the set B prime. Well, B prime, let me write this out here, and write out the definition, okay? B prime is the shorthand for the set of the universe without B in it. Gosh, I know that's a lot of new symbols. So B prime is defined to be the universe without B in it, which sounds like some sort of cheesy Valentine's Day card, really, doesn't it? Oh, the universe without you in it would be a cold and bleak and dark place. So what is the universe without B in it? Let's take the universe. I'll go ahead and write it down again. Q, R, S, T, U, V, W, X, Y, Z. And now delete every member of B, which is Q, S, Y, Z. Q, S, Y, Z. Therefore, B prime, which is defined as everything that's not in B, everything that's not in B would be R, T, U, V, W, X. So B prime is the universe without B. You could also say B prime is everything that's not in B. So the set B and B prime are kind of opposites in a way. Like if you were to think about opposite numbers, like +5 and -5, they cancel out. Well, what if we did the union of B union not B? So what happens if you take all the elements that are in B or all the elements that are not in B? What would you get?
Universe.
The universe. Right? So this idea of using a prime, that will take the universe and partition it into two parts. That's what this idea of the prime does. You take the universe and you partition it. Everything that's in B, everything that's not in B. And it creates these nice little partitions. So for instance, in this particular universe, I could define a new set V, which represents vowels. Right? So what would my vowel set be out of the universe U that we're already looking at? What's the only vowel in there? U. Not to be confused with union U or universe U, that's lowercase u. Okay, so then what would not V be? It's everything in the universe that's not a vowel, therefore it's the consonants. And so not V would be all the consonants that are in there. So Q, R, S, T, V, W, X, Y, Z. So there's two symbols then that we just introduced. One is the prime. So if I take B prime, that's actually read the complement of B. Complement of B. That's everything in the universe that's not in B. And you can also define that B prime is the universe without B. And that backward slash is the set theory symbol for without. I feel like you guys think I'm just up here making things up. Where did all these symbols come from? Well, you know what? These symbols have been around for at least 100 years, if not 200 years. So I'm not making them up. They've been around. It's just, you know, we really don't use these symbols in everyday life. Not very much anymore.
How can you know they are compared with you?
How can I know what?
For that one, B looks like a derivative, that one.
Oh, you're right. It does look like a derivative. It's the same
For that
symbol.
one?
It's a prime.
Yeah, I mean, like, how can you know there's compared with U and B?
How do I know that means the complement of B? Because we're not doing calculus right now.
No,
It's just
I mean,
context.
like, you are compare with U and compare with B and find out which they have in common, or either they don't have common. But my point is, how can you know they are compared with U? Why is not compared with A? Why is
Oh,
not
because
with
that's
C?
what the universe is there for. The universe is there to define this notion of complement. So we don't really talk about, well, I mean, you could. Here, thank you. Carmen, you could say B without A. You could say, take set B and remove from it any elements that are also in A. So you can use that symbol the same way. So you can say B without A. Or you could even say C without B. And then you would go through and you would write down what elements are left if you take all the elements of A out of the set B. So what's B without A? Let's just do it real quick. B without A, what would I have to delete? Would I have to delete the Q? Delete the Q, delete the S, delete the Y. So just Z actually. So B without A is just the set Z.
What about the W? Do we not count the W? Because that A has the W.
Right, but what we're saying is keep all the elements in B, but delete anything that you see over there in
Okay.
A. So it's merely it's a deletion process.
Okay.
So likewise, C without B, Carmen, thanks for asking this question. So you could do this. Yeah, the prime means that you're taking it away from the universe. But you could just talk about other elements where like set C, take away anything that's in B. So set C, take away anything that's in B. I would take away the Q, take away the S, I'll take away the Y, I'll take away the Z. So that's just VWX. Carmen, did that answer your question?
Yes.
Okay, good.
The under U is to take away or
Say that again?
the under part looks like an N?
No, the other up next to the universe, to the left.
To the left.
Yeah.
That's the
Yeah, this means
intersected trans.
Union. This means intersection.
So for union, it can be in one or the other. An intersection, it has to be in both.
Both, yeah. Yeah, so union means either. Intersection means both. The universe is the universe.
And all of that's your sample.
Mm-hmm.
Universe is just your entire
Yeah, your sample space, that's a good way of saying it. B complement is splitting the universe into two pieces, either B or not B. And then this other symbol here means delete. It essentially means delete. Yeah, so like B delete A. That symbol means delete. Well, that's a lot of vocabulary. You know, it's funny, in the matrix lessons that we did, there wasn't a lot of new vocabulary to learn. We all knew what a matrix was, and we knew what rows and columns were. There was a lot of heavy lifting when you were doing the actual computations and the row operations. Whereas tonight, what we're talking about is essentially very simple ideas. You have a bag of stuff, and you want to compare to someone else's bag of stuff. But we have all this new vocabulary and symbols that we're talking about. Okay, so we just did B prime. So that was B prime, or B complement. So we looked at everything in the universe that's not a B. What about B union C? Well, in that case, you just choose anything that's in either of them, right? This next one is kind of tricky. A intersect B complement. A intersect B complement. So I would always begin by writing down the problem, A intersect B complement. And first, let's just write down the set A. That's QSU. W. What? And then I want to intersect that with B complement. I already erased mine. What was the universe without QSYZ?
We're talking about B prime or B complement? RTUVWX.
Yeah, so I have to delete QSYZ. Okay, there we go. So, is that correct so far? Is that A intersect B prime?
Wait, so B is QRST, VWXYZ.
Yeah, B is just the elements QSYZ. So B prime is everything that's in the universe except delete QSYZ. Yeah, this is the set A, and then this is the set B prime. Ask your question again, Julie.
Yeah, I just like, I just,
What's that?
it's something simple, but it's just not.
Well, that's okay. Let's just look at B prime, shall we? First of all, let's just consider the universe, Julie. What's the universe? Yeah, there's the universe. And B prime, the definition of B prime is delete.
Anything that's in between B. So delete, like, so in between the B and Q, S, Y, Z, so you get rid of it.
Yeah, you get rid of the Q, S, Y, Z. That's what B prime is. Did that click?
Yep.
Okay, good. Folks, I'm so glad you asked questions because so many times it's just a matter of hearing it again or differently, and then you understand. All right, so then what's A intersect B prime? Any of you have made? What does intersect mean again?
Intersect.
Yeah, what they have in common.
Both.
That's what they
So
both
you
have.
have
So they don't both have a Q. What I do is I start just scratching it off if I don't see it over there. So that doesn't have a Q, that doesn't have an S. Oh, that has a U. Oh, that has a W. Oh, that doesn't have a Y. So I already found my intersection. My intersection is just U, W. That's all they have in common. Okay, so in theory right now, I'd want you all to like take a break, take a nap, and then come back and be like, okay, I got these symbols. But now we're just gonna go ahead and move along and try to use them.
I thought you were going to give a break.
Yeah, you'll get a break later on.
I thought right now.
Oh, no, all right, yeah. There's so much still to go. We don't want to take the break yet. Okay, folks, let's take a look at that next section. Now, fortunately, the next section, 14, 15, and 16, you don't have to write out the elements of the set. So, for instance, what's our universe? All soda pop. So all soda pop. I'm assuming that means it's a can or a bottle, and there's carbonated beverage with good, healthy, nutritious ingredients inside. Okay, so what's the set A?
All diet soda.
Diet. And set B? Cola. Meaning what? Coke, Pepsi, but not Sprite. Right? Because it's cola. That means it has to be brown. Right? That's a cola. Okay, what's that C? And cans as opposed to bottles, or soda fountain. And then what's that D? Caffeine free. Okay, so now we just described the sets in words. So what would A intersect B mean? That's soda pops that are in both set A and set B. So there's soda pops that are
In common?
Diet Cola. That would be Diet Cola soda pops. So Diet Coke, Diet Pepsi. That's really all you gotta write is Diet Cola. What about this next one? Ooh, this one's tricky. Because we're gonna do C intersect B, but then take the not the opposite, but the complement. Everything other than that. So you could kind of imagine saying this in English. I drink anything other than those. So what? First of all, what's C intersect B? What does C and B have? Or if you make it. Yeah. So in cans. And they're cola. So cola in a can. So anything other than cola in a can. So imagine that's like some cranky old man. I'll drink anything other than cola in a can. Right? Does that work? Yeah.
I'm lost.
Tell me, Carmen.
On B,
Yeah.
they did not say in
What do you mean B? What number are you?
Over there, sorry, 15.
Yeah.
They did not say in can. On B.
Set C is soda pop in cans.
Uh-huh.
And set B is cola. So what we're talking about is cola in cans. C intersect B means canned cola drinks.
I thought this one is like in common, like they both.
Right, so we're talking about soda that is both in a can and cola.
That's the inside part. The can and cola, but then you have the complement. So that makes it pretty much everything except that.
Here, Carmen, I think maybe I should include another word. Intersection means and, whereas union means or. So if we intersect, meaning and, so then literally C intersect B means C and B. It means it's in a can and it's cola. So it's cola in a can.
Oh.
And then the complement symbol means anything other than cola in a can.
Oh, got it.
Okay, good.
Thank you.
You're welcome. Okay, so what's this last one? Again, this is just enough symbols to hurt the brain a little bit. Yeah, so C complement, C prime. What is C prime?
Can.
Anything other than in a can.
Go ahead.
Right, C complement. So long as it's not in a can, and then union means or, and then what's D?
Or not calculated.
Yeah, so long as it's not caffeine free. So if somebody came up to me and said, hey, do you drink soda pop? I would say, so long as it's not in a can or caffeine free. If it's in a can or caffeine free or any combination thereof, I'm not going to drink it. It means I won't take anything in a can and I won't take anything caffeine free. And ooh, don't even try to offer me something caffeine free in a can. That would be the worst. So why is this material included in a business class? Careful thinking. It's very careful thinking because it hurts. It hurts to think about this stuff. And, or, not. This is logic. Okay, let's continue on. We got some states down there in the south. We got some Alabama, some Arkansas, some Louisiana. And we're looking at some crops. Look at all them there crops that they got. Now, as soon as we define U, they go and do something different. They say let U be the smallest set that includes all of the crops listed. Just cross out the U and make it any other letter. Make it this letter A. Better yet, make it the letter S. S for smallest. But should they have used the letter U in this context? They just finished telling us that U means universe. And now they're calling it the smallest set? Oh, terrible. So, let S be the smallest possible set that includes all the crops listed. And they're saying let A, K, and L be the set of 5 crops. Oh my gosh, actually, that is the definition of U. That is the universe. The smallest set that includes all the crops listed. Wouldn't that be the universe? Actually, that is the universe. Silly me, I saw that word smallest and I got all hot and bothered. Yeah, so what is the set U? We should go ahead and write it down first. What is the set U? We'll just list out the crops. The universe of possible crops is? Yeah, I mean, we can just start writing down. I'm going to write down all the Alabama ones first. So S, P, C, H, W. And then anything in Arkansas that I haven't seen yet. R, C. And then anything in Louisiana that I haven't written down yet. N. Like I said. Did I get them all?
But you got 2 sets of C because it's corn and cotton.
Oh yeah, but that's C and T. It's not 2 C's. That's 1 C, 1 T.
Oh,
They put two.
Yeah. Okay, so is that it? Is that the universe? Those are all the possible crops? Did we get them all? S, P, C, H, W, S, R, T, H, W, S, N, C, T. Okay.
Yep.
So that's our universe. So, okay, I take it back, textbook. You did a good job. You meant universe. So now let AKL be the set of 5 crops in Alabama, Arkansas, and Louisiana. So now find the indicated set. So what does Alabama and Arkansas have in common? What do they both make? S, H, and W? Yeah, S, H, and W. What about the next one? What kind of crops can you get from Alabama or Louisiana? Anything, anything at all. If it comes from Alabama or Louisiana, I'll take it. Yeah, anything that's not either. Mm-hmm. All right, well, that was it. That was a whole lot of setup for just 2 problems. But again, careful thinking. That's what we're talking about. Ready? Number 19, is it at the bottom? Okay. Jose is applying to college. Good guy. He receives information on 6 different colleges. He will apply to all of those he likes. He may like none of them, or all of them, or any combination. How many possibilities are there for the set of colleges he applies to? Well, folks, this is a distinctly different skill, but before I tell you how to do it, I wonder if maybe you just want to try it out on your own. What are all the different possible sets that he could apply to? Should we start by just saying that the 6 different colleges are A, B, C, D, E, F? And then he wants to start building all the possible sets of colleges he could apply to.
Oh, that's a lot.
Yeah, so much that we probably wouldn't want to write them all down. Like, it could be the set of just A, or the set of just B, or the set of just C, or just D, or just E, or just F. It could be A, B, A, C, A, D, A, E, A, F, or it could be just B, C, B, D, B, E, B, F, or it could be C, D, C, E, C, F, or it could be D, E, D, F, or it could be E, F. Okay, so that's the set of all single colleges, like, oh, I only like one college, so I just applied to 1. Or these are all the possibilities of 2. How long is my list going to be of 3? Well, I mean, probably pretty long. And then my list of 4, probably pretty long. My list of 5, maybe not that long, because my list of 5 is just a complement of the list of my onesies. Right? Because if I chose 5, that means all I did was delete 1.
Your list of 6, right? Would be the list
Yeah.
of the complements.
Right. Well, no, if I already, like my set of just 1 colleges, then A goes with the set B, C, D, E, F. That's 5 colleges he could apply to.
Oh,
And then
gotcha,
B goes with
gotcha.
A, C, D, E, F. That's the list of 5 colleges he'd apply to. So this list and that list will be the same length. And how long is the list of all 6 colleges?
1.
It's just 1 item. In any case, folks, how many different lists are those?
6 different lists.
Yeah, it's a lot of different lists. Well, how many different lists? You include 1, 2, 3, 4, 5, or yeah, 6 different lists. That's really long. How many do you think there will be? How many different subsets?
64.
64, you said? Wait, you said that?
Yes.
Oh, that's because you already did the computation? Okay.
Yes, I did it in my head. I listed them all in my head.
Yeah. Oh, very nice. Very nice. Yeah. So part of this is that you don't want to have to list all of them. If you can just know how many are in the sample space, then you can still compute a probability because you know your sample space, and then you can just say what you want. Okay, so then how do we do it? There's a notion of each element, you're going to make a decision. What's that decision you're going to make? Yes or no. I'm either going to apply to it or I'm not. I'm either going to like it or I won't. So right here, I make a decision, yes or no. And then here, I make a decision, yes or no. And here, I make a decision, yes or no. Here, a decision, yes or no, yes or no, yes or no. How many decisions do you have to make about each letter? 2. And the fundamental principle of counting states that if you list out all the decisions you have to make, which I have 1, 2, 3, 4, 5, 6 of them, and you count how many decisions you have in each bucket, and you multiply them all together, that will tell you the total number of possibilities. Much like flipping a coin. Flipping a coin. If you just have 1 coin, then it's either heads or tails, and that's 2. 2 to the power of 1. You have 1 choice, heads or tails. Whereas if you listed out the head, 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 tail, oops, tail, head, tail, tail, that was 4 choices. And that's because for each coin, it could either be flipped heads or tails, and 2 times 2 is 4. Whereas when we did 3 coins, I don't want to list it out, but each coin could either be heads or tail, that coin could be heads or tail, and that coin could be heads or tail. And so 2 times 2 times 2 is 8. I don't know if I just did that too fast.
Yeah, good.
What?
Yeah, good.
That's okay. So we're making these decisions. So in this particular case, for each college, he's either going to like it or not. And so 2 times 2 times 2 times 2, that's 2 to the power of 6, which you can do in a calculator or your head. So 2, 4, 8, 16, 32, 64. And so there are 64 different sets of possibilities. Yep, and that's how you choose it. Is that all he wanted? How many possibilities are there for the set of colleges that he applies to? Yeah, 64 different sets. What is one of those sets going to be?
So does that make it 65, or of those 64, one of them is that?
One of them is the empty set. There is a
Because
possibility.
you could, no, on all of them,
Yeah,
you could
yeah.
say no, no, no.
Yeah, there'd be no. Yeah. So the empty set is one of them. And what's the set of yes, 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 yes? All of them. Yeah. So the empty set is one of the 64. Yeah, to be sure. All right, well, that's a fun one. Now, here's Martina bought 5 books to bring on vacation. However, she decided that her bag was too heavy and she wouldn't bring all of them. How many possible subsets are there if she brings at least 1 book, but not all 5? So I'm just going to change this to A, B, C, D, E. So she's saying, how many possible subsets are there if she brings at least 1, but not all 5? So let's ignore that part for a moment. How many subsets are there? Each book, she can make the decision, yes, bring it, no, don't bring it. So what's the total number of possibilities? Yeah, 2 to the 5th, which is 32. However, she says she's going to bring at least 1 book. So are we including the empty set as a possibility?
No.
Yeah, so that's not included. And she's not going to bring all 5 books because that was too heavy. So we're not including this set either. Oops, let me see the E. Right? But we're allowing all the other ones? Yeah. Yeah, but she's considering all possibilities. She needs to bring at least 1 book, but not all 5. So how many different possible subsets are there? 32 minus 2. Yeah, 32 minus 2. So there's 30 possibilities.
Oh, I get you.
Yeah?
Is that 2 always gonna be the case and then you multiply it by?
Yep, it's always going to be the case if you're making decisions about yes, no.
Oh, because it's only a yes or no.
Yeah, because it's only a yes or no.
That's because at least 1 book, so that means that the empty set is not gonna be one of your choices. And then she's not gonna take all 5 books. So then the option of taking them all, it also is not included.
Yeah. Now, by the way, folks, this is the principle behind why Sonic, everyone's favorite fast food restaurant, Sonic, this is why they advertise something like 1 million flavor options for soda. Because what can they do with their soda? They have lots of different syrup pumps that they can put in it. So for every syrup pump they have, vanilla, chocolate, cherry, whatever, how many different syrups do they have?
1 million.
Lots of syrup. Actually, not 1 million syrups. I mean, even if they just had, let's just say that they had 15 syrups, okay? Then how many total possible ways could you put syrup into your drink? 2 to the 15th, which is what? What's the total of 2 to the 15th? 32,000. Okay, great. So that's why Sonic can advertise thousands of flavor options. All right, so they don't really have 32,000 syrups, but they have 32 varieties. They have only 15 different types of syrup, but that's 32,000 yes/no decisions that you could have made. This brings to mind a classic riddle. I'm going to tell you guys all a riddle, and you can think about it for a while. You all riddle? Ready? Okay. So, you're in a room, and in the room next to you, there are 3 light bulbs. So, 1, 2, 3. And in your room, there are 3 light switches. So, 1, 2, 3. So, you're in a room with 3 light switches, and in the room next to you is 3 light bulbs. And there are no windows. You can't see into that room from your room. Okay, there's no shadows or anything like that. So you're in this room, and right now I'm telling you everything's off. All the light switches are off. Now, you can go ahead and turn on any combination of light switches you like, and go in the other room once. And from that, you need to tell me which light bulb goes to which light switch. Because it's not like they're just in a row, like the first one goes to the first one, the second one goes to the second one, the third one goes to the third one. You have no idea. This light switch could be controlling the middle one for all you know. And that light switch could control the first one for all you know. You have no idea. So which light switch controls which light bulb? And again, the rule is, you start in this room, you can turn on any combination of light switches you want. You can go into this room once, and right then, you have to tell me which light switch controls which light bulb. And you can't go back. That's the riddle. And very cruelly, I'm just going to move on. And you can just let that simmer. Although I guess you could all just agree, is turning on one light switch enough? No, because then you only know what light bulb that one went to, and you don't know anything about the other two. Is turning on 2 light bulbs good enough? No, because then you know the one that didn't turn on the light, but the 2 that are on, you have no idea which is which. Is turning on all 3? That's not going to work either. Is turning on none of them? That's not going to work either. Okay, but there is a solution to the riddle. Carmen, have you ever heard that one?
Yes.
Okay, don't say it.
You know what?
No,
No, I don't know how to do it.
Oh, okay.
I remember like long times ago, I was in China.
Yeah.
And my middle school teacher just gave out this question. That is the question. That's all the question on their test, and then I got a 0.
Oh no, I'm sorry to bring up those bad
That's the
memories.
only question on the test. And then,
No.
Oh,
Jeez.
thank you, Mr. Thanks for bringing back memories for her.
Yeah. Lo siento, Carmen. All right, let's keep going. So, have you all seen Venn diagrams before? Yeah, Venn diagrams are a lot of fun. You know, fun, I guess that's a relative word. Venn diagrams are going to put into action the concepts we've been talking about with union, intersect, universe, and complement. So let's take a look here at what these definitions would be. So I'm going to start by drawing my Venn diagram here. Guess who Venn diagram was named after?
Diagram?
Someone named Venn. Yeah. Someone named diagram. All right, so let's see here. What would this represent? Oh, by the way, this is set A. This is set A. This is set B. And what's the rectangle?
U.
The universe. So what does this diagram represent?
A intersect B.
Yeah, that's A intersect B. I don't have that on your paper anywhere. I'm just kind of going through some basics. Right, that's A intersect B. What would A union B look like?
All the inside of the circles will.
Yeah, is that fair, folks? Is that A union B? You might just, sketch these yourself, or just looking at them is fine, but that's A union B. What would, is this one of them? No. What would A prime look like?
It's going to be everything outside circle A.
Yeah, everything outside of circle A.
Including the universe, right?
Yeah, everything in the universe outside of A. And, just anything outside of A. You're basically shading in everywhere that's not A. So that's A prime. That's pretty much the main, that's our vocabulary. That's the basic. So now we're going to move on to try these harder ones. These more challenging ones. I know, right? Isn't it exciting? Shemaya, you really gave voice to all of our feelings right then. Great!
I don't know about that.
No, it's not that bad. Okay, good. Now I can play along with you guys. So how about this first one? Ooh, see, it's already painful, isn't it? This kind of thing, it really does. It's like you just have to slow down right away. So A complement and B complement. So first of all, what's A complement look like? Now, folks, what you need to do is use crosshatch lines. So notice, I'm about to shade A prime using vertical lines only. So what's A prime?
Everything outside of A.
Yeah. Everything outside of A. And look, see, just like that. Okay? So you don't have to go crazy. You don't have to shade everything really nicely, like chiaroscuro, shading effects. So that's A prime. Is that A prime? Mm-hmm. Okay, what's B prime? We're going to do that sideways. B prime is?
Everything outside of B.
Yeah, everything outside of B. So I'm just there. Now, first of all, did you notice what area didn't get shaded at all?
The center.
Yeah, A intersect B didn't get shaded at all. Sad, A intersect B. What parts only got shaded once?
The inside of the circle.
Yeah. And now what would we call this part that's in A but not in B? That part is called A without B. Right? That's A without B, that little crescent moon shape. What would you call this part that only got shaded in B? Yeah, B without A. Right? So A intersects B didn't get shaded at all. A without B got shaded once. B without A got shaded once. So what got shaded twice?
Everything outside.
Yeah, everything else around the outside. So that's what we're asking is the intersection of A prime and B prime. So where did you crosshatch twice? That would be the universe outside of. Now you'll notice I'm just kind of shading. Now I'm just kind of shading. That was it for the crosshatching. That was your technique to get you to the answer. Now you can kind of shade in what the answer is.
So the final answer is just everything outside of circle?
Everything outside of A and B. Yep. Yeah, and technically right now I could go back and cross out my lines that I only did once. That's why maybe you do the lines very lightly so that you can always go back and delete. So that's that. How else could I have said that? Like, I'm gonna write an equal sign right there. How else could I describe where I just shaded?
The universe without AB.
Very good. You could say the universe without what? A intersect B or A or B?
Union. Does it have to be parentheses?
Well, I would put them just to be careful. Because otherwise you might think it's A universe without A or B. Right? You have to be careful about that because that means different things. So yeah, we could write the universe without A union B. And then by definition, the universe without A union B is A union B prime. Is that a fair definition of what we shaded? A union B prime. That means consider A or B, which is this, and shade everything else. All right, well, that was fun. There's always more than one way to say something. You could have said it as A prime intersect B prime, or you could have said A union B prime, and we're talking about the same region. So how about this next one? Folks, it's not obvious, but that's a prime. That's B intersect A prime. So let's go ahead and shade in B. I'm going to use vertical hatches for B. Isn't that weird? If it's a crosshatch, it's a crosshatch. But if it's just a single hatch, do you call it a hatch? Is it a hatch unless it's crosshatched? Are you allowed to say that that's a hatch? I don't think so, because there's no hatchings yet. I don't know. All right, so that's B. So where's A prime? A prime is everything outside of A? Everything outside of A. So what received cross-hatching? All of B? Yeah, just the part of B that's not A. So the crescent moon B. And how do we write that? B without A. That's the part that actually got shaded. So now you can get in there and just shade B without A. I am so going to write my wife an extra Valentine's Day card tonight that uses set theory.
Oh, no.
Oh, you know it's rich. It would be rich. I already gave her a card today. I don't see what else she could possibly want. But.
So are we doing also shade the universe part too?
What's that?
We don't shade the universe part, right?
No, because the
Okay.
universe was not crosshatched.
Okay.
No. Okay, how about this next one? A prime or B. So A prime is everywhere outside of A. Or outside of A. Or B, which is this. Now, this is tricky. Previously, up till now, we've been doing intersections. That meant we were looking at cross-hatching. But union means something else. Union means either. So anywhere you see shading now, it's part of the answer.
Union is anywhere you see shade.
Yeah, union is anywhere you see shading. And how else could we have described? Oh, whoa. Yeah, how could we go about describing what got shaded? Everything other than
Just A.
A without B. Everything other than A without B. So how would we write that? A without B, but everything else. And how do I say that? With the prime mark? Did we do it? Is that another way of saying the same thing? Nick votes yes.
So A without degree. Oh yeah, A
What
without
did we
B
shade?
would be that.
Everything
So the
other
opposite of
than
that, yeah.
A without B. Because I took a bite out of A. You know, I removed the part of B that was in it. So A without B, but everything else.
Compliment. Okay.
So is it just everything outside of them?
Everything outside of A without B.
And A without B is just this.
Yeah, so not A or B means everything outside of A, not B. Yeah. Have you ever done anything like this before?
So we taking out, so we erasing that middle part then, right?
Well, I erased this moon to show that it was unshaded.
No, she's talking about the middle, right? Where they both.
Well, the middle got shaded. Yeah, that part got shaded. That part got shaded when I shaded in B. I mean, look, I shaded B. And B was all of B. Yeah. What words are we using right now? We're using the words or, and, not. Those are the basics of logic, machine logic. And, or, not. That's how all machines and calculators and relationships work. No, kidding. All right, you did it. So, oh, did I have a couple more? There are a couple more there.
The ones with 3.
Ones with 3, I was about to say, what could make this more fun? To have 3.
We got the shade on math lab.
No, they just give them to you in multiple choice. That would be kind of fun,
Right.
What's wrong?
No, he's like going, we'll try today.
Now, folks, what's the difference between these two problems?
Oh, the
What?
prime.
C
Why
prime
the
and
prime
tri and
Oh, the intersection and the union.
Yeah, they're both of them are A, B, C prime prime. It's just that all those are intersect and all these are union.
Oh.
Because it goes A, B, C prime prime, and this is A, B, C prime prime. So we have to somehow figure out what this means.
Yeah.
So we start from the inside and work our way outside. So let's start by doing A intersect B. So what does A and B have in common? This part. We did this in multiple drafts. You don't try to do the whole thing at once. It's good to have an eraser. So there's A intersect B. Now, where's not C? Anything outside of C, right? Okay, I'm just going to wave my hand here. Anything outside of C. Where does the A intersect B intersect outside of C?
In that little portion.
that little portion.
A
Is that right?
and B without C.
Yeah. Where does A, B intersect outside of C? That's what they're saying right there. So we did the intersection of A and B. That was this portion. And where does it intersect the outside of C? Well, this is the inside of C. So that's all that's left is taking the outside part of C.
And then they want none of that.
Which means shade everywhere else.
Everywhere else except that.
Yeah. It's so funny.
Okay, so then we shade everything around it now?
Yeah, you shade everything except for that. So you would kind of just mark that off and shade everywhere else. Yeah.
Wait.
Let's do it again, but slowly. Starting from the inside, where's A intersect B?
Everything in between.
That's that part.
Now, I'm about to say and anything that's not in C.
So you have to get rid of the thinking in C.
Yeah, so we're not including things that are in C. I'm only including things that are outside of C. So that would just be that top part right there.
But since you turned it prime, it's everything that's
Outside of that.
Okay, so now what do we shade?
Everywhere else. I'm not going to shade here. I'm going to shade everywhere else. See, folks, hold on, watch. I just solved for that whole problem without the outside prime. So if I delete that outside prime, that's the answer. Ignore the outside prime, that's the answer. A intersect B intersect not C. Where's everything that's in A and B but not C? That little section right there. But now that last prime says, okay, what's everything outside of that? So we shade everywhere that's outside of that. So then you shade the rest, which I'm not going to do. Well, I mean, I can do it.
So then we
Vendría
end up
siendo, ya ves que esa era, esa
shading
del
C.
medio era.
Yeah, we do end up shading C.
That's not
Entonces,
true.
ahora con el palito te está
It
diciendo.
is true.
Entonces va a ser
So
todo
the next
excepto
one,
eso.
A union B.
So A or B.
So they would both get colored, right? Like
Yeah.
You're going to shade it.
So all this gets colored so far. Good, yeah, so folks, let's go one step at a time here. A or B means anything that's A or B. And then
B.
or anything that's outside of C. So anything that's outside of C, we now shade everything that's outside of C.
But since it's prime,
But then
now
prime would be
outside,
the
it's just the C portion.
It's just the C portion. Yeah. Yep. So I just finished doing the inside part, A union B union C prime. But then I prime that, so that means I switch my universe and I say, well, what's, to ignore all that and just see what's left, and that would be this little funny mustache figure like a white beard on Snowman or on Santa Claus. There we go. So it's just that part. Now, obviously, folks, right now we are not solving the world's problems. Right.
This is one of those where like, why would I do this?
But again, what was the theme for this lesson? Careful thinking. That's what we're doing, is careful thinking. And that does solve the world's problems. Careful. Oh yeah, I know. Well, most people don't even ever take logic. It's not part of the high school curriculum.
No, mine was in high school. Mine was validated. They take it.
All right. These last two questions are kind of fun. They're challenging us to determine if the given equation is true. So they give us an equation, and they say, is that equation true? Now, obviously, if you just want to do this on your own, you can do it on your own, but I'm going to walk through it up here after I write it down. So what is that? A union B prime equals A prime union B. Did I do that correctly? Okay. So I always start with the primes. So B prime.
Like it's a prime on
On the what?
and then
At the end of the parentheses.
Yeah.
B gear.
Oh yeah, you're right. Okay, thank you. So my first one is B prime, so that's everywhere outside of B. And then that's intersecting with A. What does that intersect with A?
Yes.
Well,
That's just the
just-
inside.
There. So far, that's what I have. It's the crescent moon of A. That is A without B. And I'm going to write that down because that's easier to remember. A without B. That's what that first one is. A without B. I'll even draw a quick little picture. Bloop, bloop. There. So now I've reminded myself the left-hand side of the equation is that. Pac-Man. Okay. Now, A prime, which is everywhere outside of A, or B, which is all of B. And because it's or, we're looking at any shading now, any shading anywhere. So fortunately, right now, I've shaded everywhere outside of A without B. And so now when I do the opposite of that, I would just be shading A without B. So was this equation true? Yeah, this equation was true.
Or I'm physical.
Now, folks, there's something interesting here about this operation called prime, called complement. It is essentially the -1 of logic. So just watch here. Look at this parenthesis here. The prime out here means to negate everything inside. So what's the negation of A prime? Just A. What's the negation of union? Intersect. What's the negation of B? B prime. Is that what we have? Yeah, so actually there's a really nice quick understanding of how to actually see that these are the same. Is by just understanding that prime means the negation. So let's see if we can just do that real quick. Can we just take this formula and negate it? That's what we're doing. So what's the opposite of A prime? A. What's the opposite of intersection? What's the opposite of B? B prime. Is that A union B prime?
No.
No. So this one's not going to work out. You can go ahead and shade the whole thing and check. But theoretically, it's not going to work out. Now that little part right there, see, that's interesting. That, first of all, you can take logical statements about sets and make equations out of them using an equal sign. And second of all, that the negation operator, namely the complement, apparently works like a -1. So somehow there is something about set notation and set operations that's very similar to arithmetic. Okay. We have a question down there at the bottom. I can barely see it. I'm going to move it back. I think that's the drawing. At East Zone University, there are 628 students in college algebra or calculus. 278 taking college algebra, 376 taking calculus, 26 taking both college algebra and calculus. How many are taking algebra but not calculus? What should we do?
So there are 628 students taking college algebra.
That's one option. We could read it again. What should we do, folks? Should we start drawing a Venn diagram?
Yes, so we put 1 section, put algebra students.
So what are our two circles going to be? Yeah, college algebra and calculus. Okay, I just did CA and calc. So which one goes in the middle? 26. That one we feel pretty good about. We know 26 goes in the middle. Now, where do we put all those other numbers? It says there are 628 students taking college algebra or calculus. What is that referring to? Is that the universe? It's the union. So if you're looking at all of the two circles together, that's 628. Both circles together is 628. Right, because that says 628 students taking college algebra or calculus. Now, 278 are taking college algebra. How do I know that? This is 278. That includes the 26 we already wrote down. Because 278 total are taking college algebra. So what should we write down? If I write down 278 right here, that's misleading. Yeah, just to subtract 26 of them. Very good. Great. I should write that different so I can actually capture all that. So 278 minus 26 is what you say? Great. And then what was the other information? Calculus, 376 are taking calculus. So 376 minus 26 is 350. So far, so good. We have 252 over here, 26 in the middle, 350 over here. What should those three add up to?
628.
They better add up to 628, or else we already did something wrong. And then we're going to send you to Guam. So that's 252, 350, and 26.
That's 628.
That's 8, that's 2, that's... Oh, good, it is 628. So what we did is correct. And the question is, how many are taking algebra but not calculus? 252. Yeah? Oh, you like this, Shemaya? Shemaya has given her approval. The test will consist of 47 questions just like that.
I said just that one.
Just that one, over and over again. All right, well, it's your luck, Shemaya. The next question is still East Zone University. Why don't you all try this one on your own? Everyone do 29 on your own. Yeah, that's the exact same level.
So the switcher is like 3 switcher.
Say that again.
Switcher is like only 3 in there. The one you just erased. Right?
Oh, the switch problem.
Yeah.
Yes, 3 switches.
Okay.
Okay, so let's see. The 510 is the total, right? And then 320 is, wait, I want to do the both first. Taking both 34. So then we have 320 over here. Minus 34, which is 286. And calculus is 224. Minus 34, which is 190. So did you all get 190?
Yes.
Okay. This is a good time to talk about the union rule. The union rule states how to find out how many are in the union. So if I add together the original numbers they gave me, 320 and 224, does 320 and 224 give me the correct total number of students taking both? 320 plus 224 is 544. Was that the correct total?
No.
No. Is it too big or too small? Too big. By how much? Which is the intersection. So if you just add together A plus B, you're overestimating the total. You have to add together A plus B and then subtract out
30.
the intersection. So that's the formal rule. This is called the union rule, folks. Union rule. I'm not talking about labor unions. So A union B is equal to A plus B minus the intersection. If you want to actually know the total of the union, you add together the two sets A and B separately, but then take away whatever they have overlapped. Because the overlap, you counted twice. You counted the overlap twice, and so you have to take away the overlap. All right. It's just a little random thing, and we'll see it again later. Okay, so here's a fun one. A survey of 280 families showed that some had a dog, some had a cat, some had a dog and a cat, had neither a dog nor a cat, and in addition did not have a parakeet. And then 9 had a cat, dog, and a parakeet. How many only had a parakeet?
See, those are the ones that don't.
There will be 17 of these on the test. Shemaya, what do we do?
We have to turn them apart. 280 is the
How many Venn diagrams do I draw?
total.
Yeah, so dog, cat, parakeet. I'm going to do dog, cat, parakeet. Now, we have to be careful because there's a lot of overlap. How do we put these numbers on the diagram so that they're meaningful? Like 107 dogs. If I put 107 right here, what does that make us think?
So I had only dogs.
That it's just dogs. But see, that 107 applies to the whole circle of dogs. And if I put 82 cats, if I put 82 right here, that's misleading because that makes you think it's just cats. But it's not. It's that whole region. So I can't put the numbers there. Where should I put it? I think next to the D, I'll put 107. That way I know that that whole circle of dog is 107. And next to C, I'll put 82. That way I know that whole circle of C is 82. Now, 37 had a dog and a cat. So where's my 37? Yeah, that middle portion right there. I don't know where to put that, guys. If we put it here, we have to remember that it applies to that whole intersection. Right? That whole intersection, not just the top part. Right? So maybe I'll switch it and use a different color. I'll say this whole thing is 37. I don't know how you're going to do that on your paper, but. Hey, if you brought some crayons with you, you're good to go. All right, 105 had neither a cat, nor a dog, nor a parakeet. So where does the 105 go? Those are for the people who don't have a cat, a dog, or a parakeet.
Would that be the whole outside?
The whole outside, correct. The whole outside is going to be 105. And then finally, 9 had a cat, a dog, and a parakeet. So where can I put that?
Is that where you take 37 minus
Hmm?
It goes right there.
Yeah, so for sure the 9 goes there. Now this is good. It was that last piece of information that's going to allow us to work backwards and out. So now that I know that this little inside triangle is 9, how much is this part above it?
Subtract 9.
37 minus 9? So that little part there is 28. Okay. And now I know about dogs too, don't I? Because if all of dogs is 107, how much is the portion of dogs that's over here, the Pac-Man? Is that what it turns out to be? Oh yeah, 107 minus 37? Wouldn't that be 70?
Yes.
So this Pac-Man shape over here is 70. And then what about cats? I can also do 82 minus 37. 82 minus 37. 45? Okay, so now that part is 45. Now just take a look at the union of A and B. Have we now accounted for all of A union B? We have. We filled in every single portion of that. So that's good. We're making good progress. Well, let's see. Did we? Oh, we didn't include the very first thing. The survey of 280 families. So 280 is the universe. So what can we do? Yeah, and that should give us the parakeets, but nothing else, right? Because we already know all those other sections. So let's try it. If we're going to add together the 70, the 37, 45, and the 105, that gives us everything except parakeets only, right? So, I need a calculator. Hmm. 70, 37, 25, 25, and then did you get that total was 257?
Yes.
Okay, so the parakeet only was 23? Are we sure?
Yeah, I checked it.
Yeah, so how many had a parakeet only? 23. Okay, well, very good. If the back of the book says it, we must be right.
No,
We worked
I
backwards.
added it all up.
You what?
I just added it all up.
Oh, okay. You mean you added those numbers?
No. I said thanks.
Oh, okay. Gotcha. All right. Well, that was fun.
So we kind of work backwards.
Yeah, well, you had to have all the information on the diagram before you can start working back out. Yeah, it's kind of like a crossword puzzle or Sudoku. You kind of work your way around the diagram until you get it. Okay. 31 is a different type of problem. They say find the number of elements in the indicated set by referring to the table. So this is H union A. So first of all, what does H represent? Hazelnuts, so all those guys. And what does A represent? Almonds. And it's H union A. So that's either or, right? So what would we do?
Add them all up.
You just add up the whole H column, add up the whole A column, and add them all together.
Like the actual numbers or 4?
The actual numbers.
Oh, okay.
What did you say, 4?
Because I was thinking year 1993 is 1.
Oh, I gotcha. Yeah, no, they didn't specify. They just said H or U. I'm sorry, H or A. So obviously you need a calculator for this. A few of the problems in here, they're a little time consuming because you just have to sit there and type it all into a calculator. Normally they're nice and they give you a totals column. They give you the totals along the bottom, they give you the totals along the side. They didn't do that for this problem. But given that it's just a matter of typing it into our calculator, how about you just circle the 2 columns and let's move on.
Can we do that on the test?
Do what, just circle it?
Yeah.
I won't give you a problem like that on the test. This next one though is a lot more exciting. Number 32, turn the page. How is 32 different?
It's Intersect.
That's intersect. Well, this is great. Now we just do the intersection of row V and column W, and the answer is immediately 230. So you didn't have to add up a bunch of stuff at all.
Wait, what is section 2? Wait, V and W. Oh.
Yeah, V intersect W. So 230 is the answer.
Oh.
Folks, we just successfully finished section 7.1 and 7.2. That's great. That's it for set theory. Set theory, Venn diagrams. Yeah. So right now, what they're assuming is we are careful thinkers and counters, that we can count things carefully. Yeah, you have to be able to count things in order to do probability. So section 7, 3, 4, 5, 6, those are all probability questions. So seeing as we just made that nice transition, should we take a break? Do you want to know the answer to the riddle or later? Later, you said? Okay.
The question is like 3 switcher, 3 light,
Yeah,
and then
please.
you only can come to that room once.
Yes.
Are they all off?
We can start with them all off.
And how many light bulb will be light?
3 light bulbs, 3 switches.
So what you want to know?
Which light switch goes to which light bulb?
Oh.
Oh, but wasn't there a door stop before? I don't remember.
Oh, everyone is gone.
Yeah. This is coming back to me. I took it like because I was going to be a teacher years ago, and when I first started, you had to do is take logic. Wow. And so when I was taking, so I'm like, look at this. I'm like, oh, I'm never going to take logic again. And now I'm looking at it, and I'm like, oh crap. I'm like, okay, that's a bitch. What?
Shit.
What did you do? What?
Just working. You guys say, save up.
Yeah, I don't smoke as often.
Hmm?
I don't smoke like that. I know. I just don't care. That sounds horrible, but.
Hmm?
No, it sounds horrible, but I just don't care.
Yeah. Hopefully get you something.
I mean, run, I'm not gonna see Black Panther tomorrow, but. Well, that's the way I look at it. My husband gets comics every week, and he gets me flowers all the time, so I'm like, or fight and clothes because I'm really sick of buying. So, yeah.
Daddy, give me something to say.
Carmen, I brought you some gifts.
Oh, thank you.
Oh, seriously, you're gonna love them.
No, I hate reading.
Well, that's what you say. So, my understanding of what you're telling people is to avoid these common fallacies, to how to avoid thinking illogically and to think logically. Right? Math is going to help you become a better thinker and a better logical thinker. Okay, maybe I'm wrong or maybe I'm right. But this book is super fun. It's called How to Lie with Statistics. And it's a common way that people get duped by advertising, media, politicians, anyone trying to lie to you, like teachers. So this is a really fun one, and it's relatively short, lots of fun pictures. It's funny, great examples. That's one. This one is the book I mentioned, How Math Explains the World. This has lots of short chapters. Bam. See, little short chapters. They're all teeny, and maybe one of those kind of applies to what you're thinking about. Okay, so you can just kind of look around. You know, don't read the whole book. And then this one is Contemporary Mathematics. Really fun. What does it say? For all practical purposes. Very practical book.
Really fun or really fun?
Really fun, Carmen. Really fun. So, now see, some of these might, you know, you look through, oh, look, linear programming. That's what we've been doing with all of our, oh my gosh, the simplex method. Oh my gosh, can you even believe it? There was an actual book that has the simplex method. Describing data, probability, statistics. What's that? Oh, competitions. Fair division. Anyway, there's a lot of fun ideas in here. I don't know if any of them are logic per se, but again, you might find something in here you find interesting.
I look at it tonight.
Yeah, so just take a look. Now, because I didn't want you to sell these on eBay, I stamped them with my personal library stamper. So.
No, I will give you back.
Okay, thanks, Carmen.
I can using white out.
Oh yeah, you could. That's why I also put an electronic tracker on them.
Oh, you did?
No,
Oh.
but maybe I did. That's the thing, you never know.
curious.
What?
Just out of curious, can we throw out the light room, then go to the switcher room?
Yeah, no. You can just go from the switch room to the light room. You're done.
If I can go to the light room first, I can just destroy one.
How would destroying one help?
Destroy one,
How would that help?
and then it won't light.
Right. I don't think that would help you identify which is which.
True.
Tell me how that helps you identify which is which. Whoa, 100 grand. That's a fun bar. What the heck? Where's Anna?
Oh, yeah, wow.
She just decided not to come?
And she says, oh, it's not a lot of homework. And she's like, I got 5 other classes and I got 3 tests next week and look at it. She didn't come today.
Oh man, not the right decision.
I was like, she probably had a whole lot of.
Anna, you hear us talking about you right now, don't you? We all think you should have come here, but we understand. We all have to make tough life decisions. I almost didn't come tonight.
Really?
No, of course
She
not.
gave us some message.
No, of course. It was never an option. I will always be here.
Can we touch a light bulb?
Yes.
Oh, okay.
Should we all hear the solution now that you heard Carmen's question? Can you touch a light bulb? The answer is yes. So what is the solution? You're in the light bulb room. No, you're in the light switch room. And you've got 3 switches. Switch 1, 2, 3. And now you've got 3 light bulbs in the other room. So 1, 2, 3, A, B, C. And you want to know which light switch goes to which light bulb. So Carmen, you're in this room. What are you going to do?
Turn one on, and then for a while, and then feel which one is. Oh, but I mean, turn one on, and then for a while, and then turn it off, and then turn the either one, the rest of it,
And then?
and then go to that room.
Right, because then one of them will be lit, one of them will be hot, and one of them will be off. And so that's how you know which light switch goes to which. You're really good, that's it. See, that's a good riddle. That's a really good riddle because mathematically there's no solution. But allowing yourself to think about the fact that a light bulb gets hot gives you the solution.
That was my middle school final.
Yep.
Oh.
Well, now you have completion, Carmen.
I'll go back and just answer that question. Say,
Yeah, you should go find your teacher.
Like, hey, do you remember like 6 years, 7 years ago?
Yeah. All right, folks, we all ready? We're all back. Let's do this. So we're starting section 7.3. It says write the sample space for the given experiment. So you're going to write the sample space for a coin is tossed and then a die is rolled. So there's a lot of different ways to do this, but I like the grid method. So if a coin is tossed, then that could be either heads or tails, right? And then if a die is rolled, that could either be 1, 2, 3, 4, 5, or 6. And so do you see every intersection? This would be H1, H2, H3, H4, H5, H6, and then there would be T1, T2, T3, T4, T5, T6. You know, H1, H2, H3, or T1, T2, T3. And so what do we mean by that? Like, what does T3 mean? Flip a tail, roll a 3.
Oh.
What does H4 mean? Flip a head and roll a 4. So does this grid correctly describe the entire sample space? Yeah. Now, when we talk about probability and coin flipping and dice rolling, we do not allow for the possibility that the coin could land on edge. Right? Couldn't it? It could. It could land on either head nor tail, but we don't really count that. But likewise, a dice you could roll it and it could fall off the table and it could land, sideways on the carpet. But again, we don't talk about that. We're just saying it lands. Okay, so is that our sample space? That's our sample space. Number 34, a box contains 3 blue cards numbered 1 through 3, 4 green cards numbered 1 through 4, and okay, that's it. That's what's in the box. So for number 34, what I want you to draw is a box, and in it, draw 3 blue cards and 4 green cards. Now I have a blue and a green marker. I don't know how you're gonna do it.
What was that?
No.
You know,
No, what you do
I
is-
don't like this one.
Yeah, so you're gonna say blue cards, so that's blue 1, blue 2, blue 3, those are my 3 cards. And then I have green cards, 1 through 4, green 1, green 2, green 3, green 4. And now, the sample space, okay, so that's just what's in the box. That's inside the box. How many things do we have inside the box? 7. The box that we just drew is not the sample space, because we haven't done anything yet. That's not the event, it's just the box. The event is that you pick a blue card and then a green card. So how many different ways can you pick a blue card and then a green card? And again, you would draw a grid. Blue 1, blue 2, blue 3, followed by green 1, green 2, green 3, green 4. And then at the
Does it matter which
intersection,
one's vertical and which one's horizontal?
What?
Doesn't matter which one's on the columns or which one's on the row.
what do you think? You're probably not. Although I guess by convention, they're saying that the blue card goes first and then the green card. So if we want the blue card to go first, I suppose conventionally, then, normally we do this element, then that element. So I probably would have switched those. But no, it really doesn't matter. But as long as you put the blue one first, so this would be B1G1, B1G2, B1G3, and B1G4, followed by B2G1, and so on. So we're just filling in this grid, and every single one of those is a possible event. That is a blue card followed by a green card. How many different possibilities were there?
Would the outcome be the same if we did it the other way though?
Yeah, it would be the same amount. If you did green then blue first, yeah, you'd be looking at basically the same events. You just switch the blue and the green.
No, I'm saying if the grid was.
Oh yeah, if the grid was switched, it'd still be the same. Yeah. How many options were there?
7.
12. There were 7 cards, but there are 12 possible events.
7 cards for 12 possible.
Oh, I mean like 7 out of 42. Oh my God.
Well, there were just 7 cards. That was just something random that they gave us. But now they're asking us to draw 2 cards, a blue one followed by a green one. And there are 12 different ways you can draw a blue one followed by a green one. There's 12 different options. So that's our sample space. You can always know the total number of items in your sample space by just multiplying the rows times the columns. So how large was our sample space here? 2 times 6, so 12 possibilities. And here 3 times 4, so 12 possibilities. How about this next one? A die is rolled twice.
Okay. So 2 times 5. Now first one.
And all you know is that the first one is a 5. This one I'm going to write down as coordinates just for fun. So the first roll is a 5. What's the second roll?
1.
A 1 or 2 or, yeah, and so on. So this also is a sample space. Or specifically, I guess the sample space would be all the different ways that you could roll a dice twice, and this is what you're looking for. The fact that the first roll was a 5. How many total possible ways are there for you to roll a dice twice? Roll it twice.
So you have
36, right? There were 36 ways to roll a dice twice. There it is. And so out of that, we're only interested in when the first one is a 5, which is where?
Yeah.
In all these. 5-1, 5-2, 5-3, 5-4, 5-5, 5-6. So what's the probability of rolling 2 dice and the first one is a 5?
6.
Yeah, 6 out of 36. Simplified to
1/2.
1/2. Yeah, exactly. All right, so yeah, this is a particular event. The event is, I want a 5 to be first. The sample space is that. The sample space is always the full universe. The event is just the thing you want, which is the definition of probability, which I erase. So the sample space is the total, the denominator. I'm gonna write that. Probability, as we said, is 1 out of total It's also event out of universe, or event out of sample space. Julie.
I just had a question in my math lab. Are they gonna accept one, like say one set, or they want us to actually list it?
I think you can just say the probability. Depends on the question. Some questions will ask you to list the sample space. And I think you'll list them as coordinates. Shia, where did you get that?
Downstairs.
What? They're still open?
Down
Wow. I didn't know that. Maybe next time you'll bring us a pizza.
Yeah, I tried to offer.
You did? No one heard you.
No, man, I did. I came in the first thing I said.
Oh, man.
I got more.
You didn't listen.
Jeez, I didn't hear it. That's a classic disagreement between my wife and I. She says, you didn't listen. I said, I didn't hear it. It's a big difference.
You were quick on that one.
Yeah.
You had that before.
Yeah, I have heard that before. All right, so we're done with that first page. Let's keep going.
36.
Yeah, so 37. 3 coins are flipped and more tails are obtained than heads. Now, hopefully, you all remember the sample space for 3 coins flipped. And you remember which arrangements have more tails than heads. So how do you get more tails than heads if you have 3 coin flips? It could, of course, be tail, tail, tail. Right? More tails than heads. What's the other possibility?
One tail.
Well, one head, right? So it could either be head, tail, tail, or tail, head, tail, or tail, tail, head. Those are the only possibilities with more tails than heads, right? 3 coins are flipped and more tails than heads. So how many total is that? 4. And how many total possible ways were there? 8. And so the probability is a half. Now, isn't that weird? The probability of having more tails than heads is 50%. The probability of having more heads than tails is also 50%. That sounds wrong, doesn't it? Yeah, but it is 50-50. So you either, can you have the same number of heads and tails? Can you flip 3 coins and have the same number of heads and tails? Yeah? Show me those coins.
You see that?
No, can you get
3
the
coins.
same number of tails and heads in 3 coins?
No.
Oh, no.
No, it's not possible. So yeah, okay. So that was, yeah, I was like, wow, those are some nice coins. Okay, when 4 coins are tossed, exactly 3 tails are obtained. So you'll notice, what did they give you there to be nice? They gave you the sample space. Yeah, the outcome. So when 4 coins are tossed, exactly 3 tails are obtained. You go ahead and just go through there and circle where 3 tails are obtained. Now let me ask you, what's easier than visually looking for 3 tails? What's easier than looking for 3 tails? Exactly, looking for 1 head. So go through there and look for the combinations that have 1 head. And how many were there? No, just 1 head.
Exactly 3.
Yeah, exactly 3 tails are obtained, which means exactly 1 head is obtained. And how many are there?
4.
I love the fact that I'm hearing a variety of answers.
4.
Because you had the sample space in front of you, and you just had to go through a circle. All right.
It's 4.
Now, why do we know for sure it's 4?
Just double check that work.
Well, you can double check all you like, but how do you know for sure it's 4? If there's only 1 head, where could that 1 head be? Here, 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 or here. How many different ones? 4. There's only 4 possible ways. But you can put only 1 head in there in the 4 different positions, right? Okay, so good. The answer is 4. Out of what?
8. No.
4 out of 16. Yeah. 4 out of 16, which is 1/2. Okay, next, find the probability of the given event. Okay.
1/4.
Yes, 1/4.
Oh. Sorry.
Okay, so now, you notice what we were doing right there is just looking at sample spaces. So now with number 39, we're technically beginning finding probabilities. We're going to be looking at probabilities for the rest of the evening. So now we're counting probabilities. Now you notice we're on number 39. There's over 100 questions. But now that we're calculating probabilities, we're done learning vocabulary and learning about set membership and all that stuff. We're just counting a probability. So what's the probability when you roll a dice that you get a 3 or a 6? Yeah, and folks, I would list the sample space. So the total number of ways you can roll a die is 1, 2, 3, 4, 5, 6. And I want to get a 3 or a 6. And therefore, it's 2 possibilities of 6. And the answer is 1/3. It really helps to draw the sample space. I really wouldn't recommend that you do any of this in your head. After all, even with that sample space, you still made mistakes. So let's definitely draw the sample space. How about the next one? A single fair die is rolled. The number on the die is not 6. So what's the probability that it's not 6? Yeah, 1, 2, 3, 4, or 5. So that probability is 5, 6. Now, by the way, I'm just teasing you guys. We all make mistakes. I make mistakes. Everyone makes mistakes because the human brain is pitiful. The human brain is not built to do this kind of stuff. That's why we have paper and pencil. Yeah, and calculators. Okay, the next one. A single fair die is rolled, and the number on the die is less than 6. So what's our? And then now it's less than 6.
All of them. 1.
No, it's just less than 6. So it's the same answer. Yeah, still 5 out of 6.
Oh, less than 6.
Yeah, less than 6.
Right.
Okay, now 42. 2 fair dice are rolled, and the sum of the numbers is 4. Now I'm not going to flip back to that screen I already showed you. If they add up to 4, what are your possibilities?
2 and 2.
Yeah, 1 and 3, 2 and 2, or 1 and 3. I'm sorry, 3 and 1. Right? Is that it? It's either 1 and 3, 2 and 2, or 3 and 1. That's the only way that it can add up to 4. So that's 3 out of. How many total rolls of the dice are there? 36. And 336 is 1/12. Now, whenever you do a probability, of course you want to simplify because that's, we always simplify fractions. Would we turn it into a decimal? Not really, because some decimals are repeating. You don't want to write down a repeating decimal. It's better just to leave the fraction. Next, 2 dice are rolled. The sum of the numbers is 1 or 5. The sum of the numbers on the dice is 1 or 5.
So they can't be 1.
Exactly. They can't be 1, but can they add up to 5?
Mm-hmm.
Yeah, how?
1, 2, 4, 2, 3, 3.
Yeah. And how many possibilities is that?
1.
Yeah, 4. So 4 out of 36, which is 1/9.
Back to the last question.
Yeah.
3 and 2 and 2. Is it 2 chance that will be have 2 and 2 at the same time?
So could it be 2 and 2, and then also 2 and 2?
Yeah.
Folks, what do you think? Should we count the roll 2 and 2 separately?
Oh.
Here's the dice. How many 2 and 2s do you see up here?
Okay, can you give us that grid too?
Sure. No, seriously, I will. Carmen, what do you think? Should you count it twice?
On here is no, but
On here is no, but somewhere else is yes?
You're saying if it gets rolled twice, right? But here both dice are being rolled once.
oh, okay, never mind.
Oh, okay, yeah.
Thank
Oh,
you.
so that's that answer? All right. Okay, then the next one, the sum of the numbers is greater than 10.
No.
So to be greater than 10 would be 11 or 12. So that'd be what, 5 and 6? 6 and 5? 6 and 6?
6 and 6. So 3 out of 36.
Yeah.
1 roll.
Folks, is probability hard?
No.
No, probability is not hard because probability is just writing down a fraction. Probability is simple, you just write down a fraction. Is counting the numerator hard? Sometimes. Yeah. The denominator is fairly simple. The denominator is the sample space. The denominator is a grid, so you just multiply rows by columns. That's the sample space. But the numerator, you have to be careful. Okay, moving on. 45. When a single card is drawn from a well-shuffled 52-card deck. Find the probability of getting a red card. Now, if you're not very familiar with cards, you should take a moment and draw the cards. Just take a moment. No, it's going to be easier than you think. It's easier. Yeah, it's easier than you think. So you would start by doing ace, 2, 3, 4, 5, 6. Look, I'm doing it. It's not breaking my hand. Jack, queen, king. And then I'm going to go, now I'm going to do this with a red marker. And then a black marker. Gosh, how do you even? There we go. And therefore, my grid now, I'm not going to fill it all in. I'm just going to make a grid so that we can all imagine what's there. See, this is simple enough.
You gonna send us that one?
I'll put it on the test. But there I'm done. That's it. I don't actually need to write everything in there, do I? I mean, we all know you just fill in your mind where the intersection is. So what is this card? 7 of diamonds. Okay, so that's it. That's all you need. You just need the sample space. So there we go. When a single card is drawn from a well-shuffled 52-card deck, find the probability of getting a red card. So how many red cards are there?
Half? Half?
Yeah, half. So half of 52 is 26, so it's 26 out of 52. You don't even really have to calculate the 26 out of 52, do you? I mean, what's the probability of getting a red card? 1 and 2. When a single card is drawn from a well-shuffled 52-card deck, find the probability of getting a 7. So
4 out of 52.
4 out of 52.
Oh, it's like this. Okay, do some more of these ones.
Yeah, sure. Yeah, we're doing a lot more like this. So that's 4 out of 52. Now, tell me, what does 4 out of 52 simplify to?
1 over 13?
And is that obvious from my diagram? I just took one whole column out of, how many columns? 13 columns. So that's obvious. If I'm taking all the 7s, that's one column out of 13, so the probability is 1/13. If I take all the red cards, that's the top strip out of both strips, so that's 1 out of 2. You can calculate a lot of probabilities just by looking at the picture without actually doing all the counting. You're just separating the diagram into parts. Okay. So I'm going to skip reading that first part, right? What's the probability of getting a club? Without counting too much, what's the probability of getting a club?
1 out of 4.
1 out of 4, right? Because you don't have to count up all the cards.
14 out of 52.
Since there's only 4 suits, it's 1 out of 4.
What is club?
This one's a club.
Oh, because I thought it was the other one.
That's a spade.
Oh,
This is a heart.
I thought that was it.
It'd be a good idea to know what they are.
Spade.
We're
It's
not
kinda
called
funny.
Clovers. Okay.
You know, I taught high school
I
for a
always
long
called them
time.
clovers.
A whole lot of kids don't know what cards are. They just don't know. They're not even familiar with them. It could be a generational thing. I don't know. Okay, well, that's it for cards now that we spent all that time drawing that little grid. So let's keep going. Everybody ready? 48. A bag containing 3 red marbles, 8 blue marbles, 7 green marbles. What's the probability that you'd randomly select a blue marble? Now, first of all, how do we draw a sample space like this? I draw a bag or a bucket. It's just 3 lines. And inside of it, without using colored markers, I do 3 red marbles by 3 R's. I do 8 letter B's for my blue marbles. And then I do 7 G's for my greens. It's just a simple sample space. Now, do you have to do that? I mean, I suppose if you wanted to cheat a little, you could just say 3R, 8B, 7G. I suppose you could do that, but some problems would be harder like that later on. So let's just see. What is the probability that the marble will be blue?
8?
How many blues are there?
80.
How many total are there?
18?
Yeah, so 8 out of 18, or 4 out of 9. Oh darn, they already changed the sample space on us. So I suppose instead of writing all that out again, which I didn't even use, I'm just going to use the cheater method. And I'll say it contains 8 red, 2 blue, and 1 green. What's the probability that it's not blue?
9,
9 over
11.
Yeah, 9 out of 11. Great. Okay, now a spinner. Has everyone played with a spinner?
what is the spinner?
A spinner is just a card that has a spinner in the middle that you flick with your finger.
Oh.
So you flick it, and then
Like
it
the one
spins
in
around and
Twister?
around and around, and then it
I was
stops.
gonna say, is it twisted?
Yeah, Twister. Yeah, it's Twister. And it says here that a spinner has equal regions numbered 1 through 21. What we're not about to do is divide out 21 regions. Right? Who wants to do that? Nobody. But you can imagine 21 regions. What is the probability that the spinner will stop on an even number or a multiple of 3? Now, in this particular case, we don't even need a picture of a spinner. We want to look at the numbers 1 through 21. We don't want to write down all the numbers 1 through 21. Let's just do one of them first. So we're looking at even numbers, and we're looking at multiples of 3. So I'm going to start by writing down the even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Did I get all the even numbers 1 through 21?
Yes.
Okay. Now I'm going to layer in my multiples of 3. So I'm going to put 3 in the appropriate spot. 3, underline my 6, 9, underline my 12, 15, underline my 18, 21. Now this is just how I'm doing it. You can feel free to do it in a lot of different ways. You could have just started writing the numbers and not written it if it wasn't even or a multiple of 3, but I think that's kind of hard to do mentally. I think it's easier to write down what you know. Now, did I even have to underline the 6s, the 12s, and 18s? No, but that's the region of overlap. So 6s are both even and a multiple of 3. 12 is even and a multiple of 3. Everything else is either even but not a multiple of 3, or a multiple of 3 but not even. Whereas the 6, 12, and 18. So what would we say then about even intersect multiple of 3? What is both an even number and a multiple of 3?
6,
Yeah, 6, 12, and 18, right? So that's the intersection of even multiple of 3. In any case, what's the question? Oh, what's the probability that it will be even or a multiple of 3? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Which is 14 out of 21. Which is,
2 hours. 3.
yeah, 2 out of 3. Now again, tonight's about careful thinking. Well, gee golly, I hope every night is about careful thinking. But we're just carefully counting, right? We're really, really carefully counting what we're talking about. Okay, each of 10 tickets is marked with a different number, 1 through 10, and put in a box. If you draw a ticket at random, what's the probability that you will draw a 3, a 4, or a 1? Well, you can all do that in your head. What's the probability you draw a 3, a 4, or a 1?
3.
3 out of 10.
Oh,
Yeah, 3 out of 10. Okay, these grid problems are really fun, where they give you a table of values. This is great. It says the age distribution of students at a community college is given. Now you notice they're just giving you the number of students, not the percent. They didn't tell us the percent. So if you choose someone at random, what's the probability that the person is at least 31? They have to be at least 31 years old. I encourage us to go back to the definition of want out of total. What do we want? What do we want? That they're at least 31 years old, right? How many people are at least 31? How many people are at least 31?
no, 86.
Oh, 18 is 20.
Yeah, at least 31. So it could be 60 plus 26. We have 86. And how many total people are at the community college? Yeah, 1123. Well, okay, that's already the answer. You don't have to type that into your calculator. You don't have to get a decimal. I mean, you can, and the answer in the back will be a decimal, but we can just leave it like that. Okay, the next 3 problems are all like that. So how about you all go ahead and try those? 53.
0.07, but they want to round it like 8%.
Well, look in the back. They probably round to 1 or 2 decimals.
Yeah, they didn't change 2%.
Oh,
They did what?
Didn't change it 2%.
Mm.
oh, okay.
Oh, they did?
They did not.
But yeah, they keep it as a decimal. Because all probabilities are decimals between 0 and 1. So yeah, try 53, 54, and 55. A lot of these questions now, we will need our calculators handy. Should we compare answers? So what is the probability that it's the degrees in chemistry or physics? What do? Add them together and divide by that. Okay. What is the probability that this randomly chosen student prefers cheese? What do you have to do? Add up all the cheeses.
And then added up all the.
And then out of everything. Now see, this is an unfortunate problem. See, they don't give us a total. It's really nice when they give you a total. I don't want you guys to have to sit there and add all these things up. I didn't even enjoy doing it when I did this before I came here. How about the last one? What is the probability that a junior prefers meat toppings? Now this one's tricky. What is the probability that a randomly selected junior will like meat? Does that mean, what's our sample space then?
Just the junior student?
Is it just the juniors or is it everybody?
Everybody.
Because had they said, what is the probability that the randomly selected student is a junior who likes meat? Then the sample space would be everybody. But they're saying, what's the probability that the randomly selected junior prefers meat out of all the
So
choices?
they're already choosing the junior.
Yeah, so the junior is set. So our sample space is just juniors. That's very subtle. Should we check in the back? Make sure that I just said that correctly? I'm pretty sure I did. But
11 over 60.
it should be 11 over, yeah, 60. Is 11 over 60?
This is all.
Over 55?
They get 0.183. Okay, well, yep.
Okay. Now, folks, for the rest of the packet, that's the kind of subtlety that we're dealing with. We're dealing with the incredible nuance of language. Because that's not very obvious, is it? What would have been nicer had they said, the sample space is just juniors? Hey, that would have been nice if they just came right out and told us that, but they didn't. So you kind of have to play with language a little bit and tease out what you think they mean. 56. What's really nice about this grid?
They give you total.
They give you the totals. That's right. That's how it should be. Don't make me add that up myself. So it shows the grades of college students in advanced math course broken down by year.
Gets it.
Use the table below to find the probability that a randomly selected sophomore gets a B.
So we're already going, choosing from the soft.
Yeah, we're choosing from the sophomores, and we're saying, what's the probability that I got a B?
So 4/23.
Yeah, 4 out of 23. Now, by the way, what were those totals? Were those totals the total number of students?
What?
These totals, they say totals percent. That's confusing. Are these percents or are they total number of students? This column adds up to 25. That column adds up to 22. That column adds up to 26. So far, so good. So the numbers are telling us numbers, not percents. Why are they telling us that they're telling us percents? Exactly. The total is 100, so it is simultaneously a number of students and a percent, because it happens that they only looked at 100 students. So in this particular case, the totals are the percents, and they are the total number of students. Again, very subtle. So what do we call these tables?
Sample table.
Look at number 57 and start reading. Contingency tables. So they call these contingency tables. It's the contingency of what you choose. So contingent upon the fact that you're looking in the region called Midwest and you're looking at Republicans, contingent upon that decision, that was 14,761 votes. So that's how they're using the word contingency. So this shows the popular votes in the 1984 presidential election. A person who voted Republican is selected at random. So who's the sample, or who's the universe, or who's the sample space? Just the Republicans.
So that's 54.
And what's the probability that they're from the Midwest? Yeah, so 14,761, and how nice of them, they already gave us the totals. So it's 14,761 divided by 54,455. So really the mathematics is not the hard part, it's knowing what you're looking at and what to choose. So that was important that we narrowed down the sample space to just the Republicans. Okay. Hey, look at that, we're on to section 7.4. Folks, I really didn't even ask you or say enough at the beginning of the class. Isn't this totally different from matrices?
Yes.
It feels very different, doesn't it? I mean, this is a very different caliber and quality. This almost just feels like puzzles. It doesn't feel like the kind of hardcore calculations that we were doing before. Okay, 7.4 is asking if events are mutually exclusive. Now, in common language, if you heard someone use the phrase mutually exclusive, what do you think they'd be talking about? A relationship. Very good. I was thinking the same thing. Like Betty is dating Bob, and Bob's like, hey, are we exclusive? Right? They're not dating anybody else. That's really not what this means here. Right? Mutually exclusive means that they can't both happen simultaneously. So for instance, can you obtain a spade and obtain an ace if you just draw a single card? Can you draw a single card that is simultaneously a spade and an ace?
No. I mean, you can, but.
Can you draw a card that is simultaneously a spade and an ace?
Yeah.
Yeah, the ace of spades. So that can happen. You can have those two things at the same time. So those events are not mutually exclusive. You can have them both. Now that reminds me of another good marriage joke. There's something about a man being right and happy at the same time. Okay, never mind. I don't remember the joke. Obtaining a face card and obtaining a 2. Are those mutually exclusive? Can you get a face card and get a 2?
No.
No, you can't get those simultaneously.
So then they would be mutually exclusive?
Those are mutually
Okay.
exclusive. You can't do both. So mutually exclusive means they can't both happen at the same time. Can I be in this classroom and in the cafeteria eating tater tots? No, that's mutually exclusive. Can I be in this room and be happy at the same time? Yes, that is not mutually exclusive, despite what some math students say. All right.
So the
So-
answer just either yes or no.
Yeah, it's either yes or no. Now that's fascinating, Carmen. Could you have something that is neither mutually exclusive nor not mutually exclusive?
That sounds like.
I don't know. That's a tricky one.
Brain twist.
It seems like yes or no to me, Carmen. I like that.
I was like, I don't know.
I'm going to think about that one. Okay, how about being a male and being a nurse? Yeah, I mean, of course you can be a male nurse. There's lots of male nurses. Now, can you be a teenager in the Senate?
No.
No, because how old do you have to be? I think to be in the Senate, you got to be
Yeah.
maybe 24, 25.
It's like the
But to be president, you have to be 35? Yeah. I think 35 to be president. Yeah.
So you know how the government's supposed to
So
send the
there's age
Congress?
limit, right?
Yes, there is an age limit. What is it? I don't know what the age limit is.
I don't
Something?
remember.
No, that's
For
But
what?
there, but there is.
I think
There
president's
is an
35.
age limit, yes.
Yeah, there are age limits. Okay,
You
moving on.
can't go and throw a party in the Senate.
I think what we're now going to do is use the idea of mutual exclusivity to calculate some probabilities. So, everybody, all right. 62. Find the probability that either a 1 or a 3 is obtained when a fair dice is rolled. Well, are those exclusive? A 1 or a 3? You can't get 1 and 3 simultaneously. So, the probability that either a 1 or a 3 is obtained, that would be what, 2 out of 6? Right. So that's just a simple problem. There's no trick question here. Now, 2 dice are rolled. What's the probability that the sum is 6 or 10?
That is not mutually exclusive, correct? You can have, I don't know.
You can get a sum to be 6 and 10 simultaneously?
No. So then why were we talking about mutually exclusive?
Because we're going to get to a problem where it doesn't.
Oh, okay.
So, can you get a sum of 6? Right here they are.
Yeah.
How many are there?
5.
5. And how many rolls of 10? 3. And yeah, they don't overlap. You can't simultaneously add your dice together and it equals 6 and 10.
What should it be? 36.
So what was the probability?
830, is it 36?
It was a 5 and 3, 8 over 36. Okay, but now, find the probability that the sum is at least 10. Well, I think we've already done this one. The sum is at least 10? That'd be,
Are 2 dice probably? Oh, yeah.
yeah, 2 dice. So actually, I mean, that's a lot of possibilities. You could have a roll of 10. Yeah, at least 10. So 6 and 4, 4 and 6, 5 and 5. Or it could add up, right? Yeah. Or it could add up to 11, 6 and 5, 5 and 6. Or it could add up to 12, 6 and 6.
Oh, yeah, we did this one.
Yeah, I do feel like we did this one.
6.
So anyway, it's
4, 5,
6 out of 36.
6, 7.
Those are all the ways that dice could add up to 10, 11, or 12. Yeah, actually, these 4 problems had nothing to do with mutually exclusive probability. That's just a little strange out of order. So a card is drawn from a deck. What's the probability of drawing an ace or a 9? How many aces are there?
4.
How many 9s are there?
4.
Now, don't add 4 plus 4 to be 8 out of 52. How many columns did I just choose? 2 columns out of 13, right? I mean, you could have just done 4 plus 4 is 8 divided by 52, but then you'd have to simplify the fraction. 8 out of 15 is 2 out of 13. So you could just say that's 2 columns out of 13. So 2 13ths. Okay. Okay, maybe it is next problem. So when 2 balanced dice are rolled, there are 36 possible outcomes, and we've seen those. Find the probability that either doubles or the sum is 4. Okay, so now I'm going to go back and show this. There. So either what? Doubles? Are these, well, should I go all the way to here? Well, no, I'll stay here. Doubles would be the diagonal, right? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So how many of those are there?
6.
6. But then what? The sum of 4?
The sum is, or the sum is 4.
Yeah. So we did have some overlap there. Because one of them,
Oh.
the sum of 4,
So is that
was a double. So that's what they mean about mutually exclusive. You could be both a sum of 4 and a double simultaneously. And so,
count that as 8 and not 9?
right, so that's only 6 plus 2 more, that's only 8. That's only 8 total possibilities. You'll also notice, because there was overlap, remember the rule of unions? A union B is A plus B minus the intersection of A and B. So the total number of doubles was 6. The total number of 4s was 3. But how many did they overlap at? 1. So that was 6 possibilities along the diagonal, 3 possibilities for adding to 4, but one of them they overlap, so you have to subtract the one out. That was the rule of unions I mentioned a while ago.
What was number 66?
I don't know.
Yes.
That's in the question says 2 9.
It says what?
2 9.
Well, let's see. This is 8,
Divided
36.
by 4, yeah, 2 nights.
Yeah, 2 9s. That is correct. Thank you, Julie, for checking. So let's see. I'm not going to keep flipping back and forth here. What number are we on?
We are on 67.
Okay. So on this next one, 2 dice.
Roll.
That the first one is a 3 or doubles.
First one is a 3, so then that would be 6.
So first one is a 3 is this whole row. Or doubles, which is the whole diagonal. So how many start with 3, the whole row?
6.
That's 6. How many diagonal?
6.
6.
But
And they
one
overlap
repeats.
at once.
So 6 plus 6.
So it's 6 plus 6 minus 1.
36.
Yeah, 1136.
What was this one called? The union something?
The rule of union. The union rule. It's one of those. Union rule. You add them together and subtract the intersection.
8 of 36 because there were 6 probability doubles. So when you look at this one, the doubles, it's going to be when you have 1, 1, 2, 2, 3. Ay.
Oh, double.
Double means
I
they
thought
fit the
it's like
same.
the first one is 3 and the second one.
Oh, it's 3 and 6?
Yeah.
Oh,
What
okay.
is it called?
Oh, like
That
twice
Double
the
means
amount.
Yeah.
Then what is it called? If
Doesn't
one-
call anything.
It's just twice the amount. It would be like
Twice
twice.
the amount.
If it was 3 and a 6, that would be the second one is twice the amount of the first one.
Oh,
Because then that when you it would be 3 and 6 and 2 and 4, or the opposite.
Okay. Thank you.
Not
Okay.
usually.
Now 68, back to the spinner. We don't actually have to draw the spinner, but now let's try to be, instead of listing it all out, let's try to be strategic. It says, what's the probability that the spinner stops on an even number? So first of all, how many even numbers are there?
We have 2, 4, 6, 10, 12, 14.
Is it 7? Okay. How many multiples of 3 do we have?
2. Oh wait, on the total from 1 to 15?
Total, yeah, we're gonna use the union rule. Instead of looking at overlap, we'll just straight up count both of them. So there were 7 even numbers, 5 multiples of 3, and then how many of them are even and multiples of 3? Now what does that mean? If you're divisible by 2 and 3, that means you're divisible by,
1. I'm saying, I was just saying number 1.
if you're both divisible by 2 and 3, that means you're divisible by 6. Because 2 times 3 is 6. So how many multiples of 6 are there?
2.
2 and 12. So that's 2. So the answer would be 7 plus 5 minus 2, which is 10. Now that was nice and helpful because we didn't have to sit there and list them all out like last time. Listing out all the evens and then listing out the multiples of 3, and then we would have noticed that overlap though, wouldn't we have? We would have noticed the overlap of the evens with the multiples of 3 that were counted twice, and we would have just subtracted them. Okay. Now folks, this next section is a totally different concept, and it's called the odds. Surely you all have heard of this concept of what are the odds? I mean, that's just a phrase. You know, you walk into the room, and your enemy is there, you want to avoid them, you're like, oh man, what are the odds? Or something like that. So what is the actual definition of odds? Like, let's say you're betting on a horse race, and they say the odds are 5 to 2 against you, or the odds are 5 to 2 for you. What on earth does that mean, 5 to 2?
5 out of 7 or 2 out of 7?
Yeah, that'd be true. Yeah, when we look at 5 to 2, first of all, we express odds with a colon, and we say the word 2, T-O, so it's 5 to 2 for you or against you. The 5 is what you want, and the 2 is what you don't want. And therefore, the total is 5 plus 2 is 7. So what this really means is that the probability of you getting what you want is 5/7, and the probability of you not getting what you want is 2/7. So that the odds, whenever you look at the odds, when you add those two numbers together, that's the total number of things that could happen. And so they're really, what are they really doing? They're telling you both probabilities, but they're just not telling you the denominator, right? Because we got to make it easy for the masses. We can't go around saying you got a 5/7 chance of winning. No, we would just say 5 to 2.
5 to 2.
All right?
Like they sound a lot.
Yeah, exactly. 1 in a million. That's what does that mean? 1 ticket will win and 1,000,000 tickets won't win. All right, so that's odds. Find the odds in favor of spinning an A on the spinner. So we're going to say the odds are what you do want, colon, what you don't want. So how many A's are there? 3.
Oh, snap.
And how many total?
It was this one.
Well, no, I'm sorry, not
No,
total.
not total.
How many are not A? 5. So the odds are 3 to 5 in favor of you getting an A. Of course, 3 to 5 in favor is not very much in favor. The odds are stacked against you. So what's the probability? 3/8 and 5/8. Right? Because you just add those two numbers together, that gives you the total. So this is how we say odds. What are the odds in favor of drawing a 2 down there? 1 to
4.
1 to 5.
No, 4.
Oh, you're right, 1 to 4. Yeah, because there's one thing that you do want, which is drawing a 2, and then 4 things you don't want, which is every other number there. So the odds are 1 to 4, but that really means you have a 1/5 probability of getting what you want, and a 4/5 probability of not getting what you want. What are the odds in favor of drawing a red marble when a red marble is selected at random from a bag of 2, 5, and 6? Now you notice it feels like we've spent the last half hour just asking lots and lots and lots of probability questions. Right? We're just carefully thinking about our sample spaces and our sample sets.
Okay. Where are we at here now? Find the odds in favor of drawing.
So again, for number 71, you at least want to draw something to show 2 yellow and 5 red and 6 green. And the odds in favor of drawing a red would be what?
5/8.
Yeah, 5 to 8. Now you might notice that this feels even easier than doing probability. Because all you got to count is what you want and what you don't want. And you don't even have to count the total. Although obviously, as soon as you know the odds, you can easily calculate the rest.
You're like,
Maya,
roll, I got this.
What's the probability that the test will be like this?
I'm 100%.
Are the odds in your favor, Shemaya?
Very
Okay. Now, we started the class talking about probability as a decimal, and now finally they're doing it for us. Here they've given us probability as a decimal. You've noticed that every single decimal is between 0 and 1. So it shows the probability of a person accumulating specific amounts of credit card charges over a 12-month period. Find the probability that a person's total charges during the period are 400 or more. So you can just look. What's the probability that you spend over $400?
0.15.
Yeah, 0.15. Well, that was just too easy. Below is a table from a survey given to 1,600 teenagers. Why do you suppose they did 1,600 teenagers? It's a nice round number. It'll be evenly divisible later on. Estimate what % of their classmates are using drugs. Now this one's fascinating. I don't know if this is true or not. But this is just a survey of what teenagers think their classmates are doing. So if a girl is selected at random, find the probability that her estimate of the percent using drugs is 50% or higher. So there's the girls, and 50% or higher is 166 plus 7. So what is that? 173? Out of what?
I don't.
Yeah, see, why don't they give us totals? I don't understand.
Oh, I have to add them.
Nobody wants to do that.
Seriously.
Seriously. Who wants to add all that?
Boys and girls?
Well, now that's a good question.
No, it'd just be girls, right? Because they say if a girl is selected,
Yeah, what is the probability that her estimate? So
so the girl becomes a sample size.
I think I would agree. But we're just looking at girls. So
800?
now 800, that's an obvious total. What did they do? Out of 1,600 teenagers, they asked 800 girls and 800 boys. And so 173 divided by 800 is 0.216. Now, obviously, if you were going to give this table to someone, what would you give them? Would you give them the numbers? Or in each cell, would you just give the probability?
Probability.
I mean, yeah, probably just the probability. But
Unless you want to use this number for something else.
see, that's challenging. Because what would I put for the girl spot right there? Well, see, that's both of those combined.
Yeah, I like that better.
And that was the sample space of just girls. Had I done the sample space of boys and girls, that'd be a different number.
Mhm.
So maybe this is the only way we can do it. Well, no, you would still just do it out of total. You could do it, and that's a different type of problem, and hopefully we'll get to something like it. Are we all on 74? So a student from a college is selected. Find the probability that they're between 26 and 35 inclusive. I feel like we've already done a problem like this.
Yeah.
I mean, at this point, we've done a lot of these types of
Oh,
problems.
yeah, we did.
And I feel like we're probably ready for
Student
something
is
new.
between 26. Okay, yeah, so it'd just be those two.
So what, 254 divided by 1,083? So roughly a fourth, roughly 0.25. All right. So section 7.5.
We're in home search.
Yeah, we really are. Well, we already know the definition of odds, so this should be fairly simple. If the odds in favor of winning the horse race are 7-2, that means 7 wins versus 2 not wins. Find the probability that the horse will win.
7 8.
Yeah, 7 out of 9. Because you add up the 2 numbers in the odds, that's your total. So 7 9s. The odds in favor of Carl beating his friend are 5-2.
That's
That means-
rounded.
What?
Sorry, I'm 74. I was like, that's how you round it.
Oh, okay.
Oh.
Oh, yeah, they might have rounded. There's 5-2. Find the probability that Carl will win. So that'd be what? Yeah, 5 out of 7. The odds against Carl beating his friend are 6-5. So now you have to keep in mind that that 6 represents what? Him losing.
Oh.
So find the probability that he'll beat his friend. What number do you have to look at? A 5. So that's 5 out of 11. So that's very.
It's what?
That one would be 5 out of 11 because the odds against him beating his friend are 6. So that's him losing. So the probability that he'll beat him, that's the 5 out of 11. Okay. Okay, now here we go. Here, we're getting to some really good stuff here, folks. 78. Now, we're about to do something completely different. Completely different. Now, I'd be interested in just hearing what you think. If a single fair die is rolled, find the probability of a 4 given that the number rolled is odd. This problem is just silly.
One.
Given that you just rolled an odd number, what's the probability that it's a 4?
0?
0. Right? Hey, that was just a silly problem. That's silly. Find the probability of a 4 given that the number you rolled is odd. Well, that's just impossible. But what's important is this new phrase they just used with us, given that.
You know what I thought it meant when you said that? Is
What?
out of the number of the dice goes up to 6, and out of it being odd, it started at 4. I was
Oh,
thinking that would be it.
I see. All right, so let's try another one. Given that. Let's just read it once. If 2 fair dice are rolled, find the probability of a sum of 6, given that the roll is a double. So what is the phrase given that doing for us? The phrase given that is changing our sample space. That's in fact our new sample space. So normally if we were to do a problem with 2 fair dice, how big is our sample space? 36. But they're saying here, find the probability that you get a sum of 6, given that the roll is a double. So we're only considering doubles now. That's our sample space. If we're only considering doubles, how many doubles do we have?
6.
6. And what was the question? The sum of 6. So that's just this one. So what's the probability of getting a sum of 6 given that it's a double?
1 out
Just 1 out of 6. So this phrase given that is changing our sample space. It's narrowing our sample space. It's going from the big universe, the big sample space, and making it smaller, and then we have to do the probability out of that.
Okay.
So that's what the word given that means. So how about 80? If 2 cards are drawn without replacement, now without replacement, we have to talk about that too. Let's say I had a deck of cards here, and I draw one, and then I put it back in the deck when I'm done. That would be with replacement. So if I have a deck of 52 cards and I draw one, and I put it back in, how many cards are still in my deck? 52. But if I do without replacement, and I draw a card and I look at it and then I throw it away, now how many cards are in the deck? Only 51. So without replacement means you're removing things from the sample space. So if 2 cards are drawn without replacement, find the probability that the second card is a spade, given that the first card was a spade.
So you have
Close. So the given that, remember, given that reduces our sample space. So what did we just remove from the sample space?
all the rest of them. We have
Just a single spade.
But you have 2 cards that are.
Yeah, you're drawing 2 cards without replacement. That is, you draw one, throw it away, draw another one.
So.
Yeah, throw it away. So the first card that you drew was what?
space.
A spade. And now that, okay, so let's just consider what we have left then. You start with an original deck. Here, this is the original deck. The original deck had what in it? 13 spades and 52 cards, right? This isn't necessarily a fraction, but I'm just writing the information. My original sample space had 13 spades and 52 cards. Now, the first card was a spade. So I'm going to take that out of the deck. Now what do I have left? 12 spades and 51 cards. Now, right now, okay, so now this is my new deck. What is the probability of drawing a spade?
Add them together.
And 12 out of 51. Is that what you said, Nick? Oh, okay, you got it.
I think that's what he said.
Yeah, there you go. So that's the probability of getting a spade, given that the first one was a spade. So again, what does given that mean? It's your new reduced sample space. That's key. We're shrinking our sample space to only consider a smaller subset. Okay, the next one. If 2 cards are drawn without replacement, find the probability that the second card is a face card, given that the first card was a queen. So again, let's look at our original deck. The original. The original had 52 cards. And I suppose, how do we show that we took out a queen? I mean,
Oh, 3?
our reduced sample space only has 51 cards. And we removed a queen.
Yeah, but so they're all face.
What's that?
The second is the face. The first is the queen.
Well, but this was just my original deck.
Oh,
So then the first thing I did was, given that the first card was a queen, so I removed a queen from this deck.
So now we have 51.
So now this is my sample space. Okay, so now what's the probability of drawing a face card?
Now we're gonna go all the way from.
So how many total face cards do we have?
12.
12. But we removed a queen, so we only have 12 and 51. That's the probability of drawing a face card. Sorry,
Wait, no.
11.
Uh-huh.
Yeah, thanks guys, 11. So there are 11 face cards left out of 51 cards left. Okay, we finished both of those, right? Okay. Assume that 2 marbles are drawn without replacement. So again, without replacement, what does that mean? You take it out and you throw it away. You take it out and you throw it away. Row of arcs with, so we have to draw this. Really important. I mean, I don't know if you think I'm like a little caveman up here, but drawing out my blue, 3 white, 2 green, to red. Oh, well, this wasn't even a given, that problem. Oh, well, kind of it is, because we still have to go one at a time. Find the probability that both marbles are red. So what's the probability that the first one is red? So we're going to do our first choice and then our second choice. Because we can't just say 2 out of, what is this, 1, 2, 3,
8.
7, 8. We can't just say 2 out of 8. That would be the probability of getting a red on your first draw. So in fact, that's part of the problem. What's the probability that both marbles are red? Again, remember, you're going to draw out one marble, look at it, throw it away. Now draw out another marble, look at it, throw it away. So what's the probability of getting a red my first time?
2.
2 out of 8. Now take it out and throw it away. Now what's my probability of drawing a red?
1 over 7.
1 over 7. And now what do we do with our probabilities? We usually don't add them. We multiply them. Now that was a good guess. It could have been add or multiply, right? In this particular case, it's multiply. Now here's a good reason why we know it's not add. Because what if I had said, what's my probability of getting, oh, let's say, white or green? So that would have been 5 out of 8, right? And then I take 1 out. What's my probability of getting white or green now? 4 out of 7? Well, what's 5/8 plus 4/7? More than 1. So that would put our probability over 1. And yet that certainly is not a sure thing that I would have drawn a white or a green, right? So it's not adding the probabilities, it's multiplying. Multiplying them also makes sense if you think about the 2s that we did earlier. When you have all those decisions of turn the light switch on or off, turn the light switch on or off, turn the light switch on or off, we were multiplying the 2s. In most situations, probability is multiplicative. And I'll tell you more specifically, it's multiplicative when there's the word and. So this problem was find the probability that both marbles are red. That means that the first marble is red and the second marble is red. So and means multiply. Okay, well, did we get our answer? 128?
Why this question we should multiply together? The last question we did not need to.
Because here we're using the same one.
We use the reduced sample space because the previous problem said given that. Given that. So that was already done. It's the past.
Oh.
Yeah, given that it's already done, it's the past, there's nothing you can do about it. It's not part of the current situation. Here they're saying, I want you to do this experiment where you draw 2 marbles. So here, you were really doing just one experiment, the second card. I know that's very subtle. I don't know if my explanation is sufficient for you. All right, ready to try the next one? Is that the same sample space? 1 blue?
31, 2, 3.
Yeah, it is the same.
And 2 red? No. Oh, yeah, now it is, because I think before this.
Okay. Well, now, this is more of the same practice. Find the probability that both marbles are green. So the probability of drawing the first green is 2 out of 8. Now you remove that green, what's the probability of the next green?
1 over 7.
I'm saying, okay, well, that's exactly the same problem.
Multiply.
Yeah, and then you multiply. So that's still 1 out of 28. Okay, 4. Same sample, no, not the same sample space. No, same sample space. Find the probability that 1 is green and 1 is red. Now this is different. 1 is green and 1 is red. Now, if they're just saying that 1 is green and 1 is red, what are our options? Maybe the first one was green and then the second one was red. Or what? The first one was red and the second one was green. Now listen, look very closely at the words I'm going to write down. I hope you write this down too. So our options are red and green, or green and red. Isn't that what we're looking at? Because they're just asking us, find the probability that one of them is green and one of them is red. So that could have been drawing the red then the green, or that could have been drawing the green then the red. And you'll notice now I just used the words and the word or, which goes all the way back to our logical intersection versus union. Okay, so what's the probability of doing red then green? So what's the probability of red? 2 out of 8. Followed by green now, which is 2 out of 7. Okay. Now, go on to the second experiment. What's the probability of getting green first? Still 2 out of 8. And then red? Also 2 out of 7. Now, the and word means multiply. So I'm going to multiply these probabilities together to get, oh geez, 114.
Yeah.
And I'll multiply these guys together to get 114. But now the word or means add. So an and means multiply and an or means add. Whoops. So it's 1/14 plus 1/14, which is 2/14, which is a 7th. How do you all feel about that one? First of all, was it the answer?
Yes.
Yeah, it was the answer. And so this is just part of our learning of new terminology, that in a probability problem, and means multiply, or means add. Okay, and now we'll definitely continue to use that right now. In 85, 81% of scheduled flights actually take place. And they're telling us that cancellation are independent events. What does that mean, that a flight cancellation is an independent event? So my flight to Ohio just got canceled. And somebody else's flight to Texas got canceled. Did those two things have anything to do with each other? No, that's what they're saying. They're saying that cancellations are independent, that they have nothing to do with each other. Is that in real life? I mean, maybe not. If there's a huge storm in Phoenix, then there's a very good reason why no flights are going out, because there's a storm in Phoenix. So they're not independent events. But they're telling us to assume that in this problem, 81% of scheduled flights actually do go, and that cancellations are independent. So what is the probability that 3 separate flights will all take place? So this is a counting problem, as before, where we had our buckets. Here's the first flight, the second flight, and the third flight. And what's the probability that the first flight will go? 81%? That's the probability that the first flight will go. What's the probability the second flight will go? Also 81%? And what's the probability the third flight will go? Also 81%, yeah. And so we're saying and. We're saying the first one will go, and the second one will go, and the third one will go. And means multiply. So it's really 0.81 cubed. And that is the probability that all 3 flights will actually take place. Which is? 0.531. 0.531. So just over 50%. Now, right now at this moment, I suspect maybe you're thinking, oh, geez, you're really throwing a lot of different things at me. How do you remember when you add? How do you remember when you multiply? You know, there's a lot of different scenarios, isn't it? And in the beginning, I wish I could tell you hard and fast rules. In the beginning, you know, it's just being exposed to all these different possibilities. And over time, you build an intuition. But as much as possible, I'm trying to give you rules. And some of those rules come back to the language of and or. So let's try again. If 2 cards are drawn with replacement, now what does that mean? You draw a card and then you put it back. So your sample size started at 52, and now it's still 52. So 2 cards are drawn with replacement. Find the probability that the first card is a heart and the second is a diamond. So I'm going to go over here and look at my sample space here. What's the probability that the first card is a heart?
1/4.
1/4. So what's the probability the first card is a heart, and the probability that the second card is a diamond?
So we're just looking at the actual Shoots of the cards, not the whole.
Well, you can look at the whole thing if you wanted to. I mean, the probability of getting a what? A heart? That's 13 out of 52, which is 1/4. Yeah. And so the fact that that word is and there, that's key. The and is telling you to multiply. That's saying simultaneously. It's got to be a heart and then also what? Diamond. Oh boy. Read this next one. This feels very different. The family has 5 children. The probability of having a girl is 1/2, and therefore the probability of having a boy is 1/2. What is the probability of having 2 girls followed by 3 boys? What's that? Oh. So we're having 5 kids, and we're going to have 2 girls followed by 3 boys. What was the probability of having a girl? And the probability of having a girl? And the probability of having a boy? And of having a boy? And of having a boy? So what's the probability of that particular pattern? 1, 2, 3, 4, 5, 2, 4, 8, 16, 32. So the probability is 1 in 32.
That's something.
Yeah. Now, the first thing you might say, well, gee, it seems like any combination of kids is going to work out to be the same probability. I mean, what if I had said, what's the probability that it goes girl, boy, girl? What would the answer have been? Still, it would have been 1/2 to the power of 5, right? So is every possible sequence of kids that you might think of, is that probability always 1 in 32? Because what are we really thinking about? We're looking at every possible collection of G's and B's, which remember is tails and heads.
Yes, no.
Yeah, yes and no's. And so every possible unique sequence is one sequence out of 32 that could happen. So yes, any given ordering of boys and girls is going to be a probability of 1/32, because there are 32 different ways to flip a coin 5 times. You'll notice that here I put in the 1/2. What if I had just asked how many different possible sequences of girls and boys are there? How many different sequences of girls and boys are there? How many options are there for the first child? 2. 2. For the second child?
2.
2 and 2 and 2 and 2. What's so funny about that?
I don't know. She laughed and then
Like, what other options can you get?
I mean, there are a lot of options these days, but there's still always got to be boys and girls. Okay, so that's how many different possible sequences of boys and girls there are. So this particular sequence is just one of them, so the answer 1/32 is reasonable. Okay, folks, we're on the home stretch. Would you believe it? I mean, I always believed this moment would come. I knew we would get here with 15 minutes to spare. So we're going to go back to something I mentioned at the very beginning, which is a tree diagram. So let's take a look at what they're saying here. 45% of stores' computers come from factory A, and the remainder come from factory B. So, of A store's computers. So you got a store. I don't know what store it is, but they buy computers from factory A and from factory B. So everybody, let's start by doing a little dot and make a branching tree. Either it came from store A or store B. Now, 5% of the computers from factory A are defective. So I'm going to come up here to A, and I'll give 2 branches. And what do those 2 branches represent? Defective or not defective. And then it says 2% of the computers from factory B are defective. So now from factory B, we also have defective and not defective. Now what we just drew is just the tree. We need to go back in and layer in all the numbers now. But it's nice to draw the tree first, just to know what you're looking at. So 45% of the store's computers come from factory A. So factory A is 0.45. That's the probability that a computer came from factory A. So what's the probability that it came from factory B? 0.55, right? Because in this case, the probabilities have to add to 1. The computer had to come from somewhere. And so 45% of them come from there, and 55% of them come from there. Now, going back to factory A, 5% are defective. So now my defective is 0.05, and my non-defective are therefore 0.95. Again, 100% of their computers are either defective or not defective. And then 2% from factory B are defective. So you've got 0.02. Now I don't really want to finish reading the question yet. Let's just take a look at what we've done. We made a really nice tree. And so our possibilities are a computer from factory A is defective, a computer from factory A is not defective, a computer from factory B is defective, or a computer from factory B is not defective. And to get to the end of each branch, you multiply the probabilities along the way. So I would like us to go ahead and use your calculator and put the resulting probability at the end of each branch. Because that will tell us the overall probability of ending at the end of that branch. Keep all the decimals, because there will be a few. Now again, don't read the problem yet. We're just exploring this idea, this new world that we're just discovering right now, which is tree diagrams. What do you notice about the probabilities of the top 2 branches?
Add up to.
Yeah, they add up to 45. Does it make sense that they would?
Mm-hmm.
Because after all, what did the 0.95 and the 0.05 add up to? 1. And so multiplying 0.45 times a collective of 1, that should be 0.45. And what do these bottom 2 add up to?
0.55.
Yeah, 0.55. And therefore, what do all 4 add up to? 1. So this is really nice. The tree diagram is really nice. All 4 of these are going to add up to 1. And each branch kind of adds up to the previous branch that it came from. So these 2 add up to 0.45, and these 2 add up to 0.55. This is really handy. Okay, well, I'm sure there's more we could talk about from this, but now let's read the question. If one of the store's computers is selected at random, what is the probability that it is defective and from factory B? So they're just going to take one computer at random, and they're just wondering, gee, what are the chances that it's a factory B defective computer? It's and remember means multiply. So it's from factory B, and it's defective. And so the probability is that one. Now, I'd like you just to make up a couple more questions here before we move on, because we just spent all this time making this tree diagram, so let's not move on just yet. What if I asked you the problem, what is the probability that it is defective, given that it's from factory A? So given that it is from factory A, okay, that's a given now. It is an absolute given that we're from factory A. What's the probability that it's defective?
5%.
What, 5%? Just the 5%, because now this branch is taken for granted. We're already here. So now the probability that it's defective is just 0.05%. Is that fair? So the given that, what did the given that do? It reduced my sample space. It reduced me down the tree. So now I'm just here. How about, what's the probability that it's not defective, given that it's from B? I mean, given that it's B, So now it's 98%. So when we use the word given that, what are we really doing? Yeah, we're reducing the sample space. We're moving further out into the tree. And now we're just considering the branching that's left over. Or, which is what this problem did, you could just use the word and. What's the probability that it's defective and B? Now that's very different. Given that it's defective and B, that means we're going to multiply those two events. So it's B and it's defective, so that's 0.01.
If it was that it's defective, period.
That's a great question. What's the probability that it's defective? What's the probability that it's defective?
We add those two.
Exactly. You would add those two together. So the probability that it's defective is it's this one or this one. And or means add. So the probability that it's defective would be 0.0335?
225.
Yeah. What? I got 0.0335.
Oh, you added it already.
Yeah, I added it already. Okay, great question. What's the probability that it's not defective?
So then we do the 0.4 and the 0.5.
Yeah. Which, I don't know. 9665? Did anyone? Okay. These are all really good questions. Are there any other good questions or any other questions we can ask? We said, what is it? What is the probability that it's defective? What's the probability it's defective given that it's A? Or given what's the probability it's not defective? What's the probability it's not defective given B? Is there another type of question we could ask?
What was the first one?
What was the first one?
Proposition of defect in B was it 0.11?
Oh yeah, it's 0.011?
Yeah.
What's your question?
Yeah, I think that's, yeah. I was just making sure I have it right.
Okay. Well, there's one other question we could ask. What other use of language did I say up here? I said defective given that it's A. Not defective given that it's B. What could I have said? What? No, go ahead, Julie.
I was thinking B defective given.
What about switching these two? What's the probability that it's A given that it's defective? We didn't go in that order yet. Okay, and that last idea is called Bayes' theorem. So I want to share it with you before we move on. Let's all think about this. What's the probability that it's A, that the computer came from A, given that it's defective? So, what are we interested in? We're given it that it's defective. That's our sample space. Our sample space is the fact that it's defective. So where's defective? That one. So we're going to start calculating the probability here. My sample space is those two added together. Because I'm giving that it's defective. So it's one of those two. So let's add those together. That's 0.0335. Now, out of those two branches, which one am I interested in? The probability that it's from A. So that is the probability that it's from A. And that's what I want. 0.0225. Now, that's just a slightly different type of problem. What's the probability that it comes from A, given that it is defective? So now we know it's one of these. And I want to know that it came from here. So it would be this divided by the sum of both of those. That's called Bayes' theorem, B-A-Y-E-S. And that's the last section. Now, obviously, my phone just gave off, which means we have 20 minutes left. No one look at your clock. Okay, so, well, I'm pretty sad. I mean, we did run out of time. I don't want to keep anybody late. Oh, gee, no. We weren't going to do all of these. We'll simply run this over into the next class. Okay, because we have a little bit of flexibility here. We just have all these class periods left, so no biggie. We'll just start back up here from next time.
Okay.
You'll all go home and have dreams about this.
Yes. Sure. That's some probability.
You will.
Seriously.
We have enough math lab problems to figure it out.
Yeah, you can go do all the other ones first.
Oh, do you have chapter 8?
I'll have to mail it to you.
Okay,
Yeah, I didn't get to print it out.
that's fine.
I like it.
Thank you. Monday? Oh, sí, cierto.
Lorena, thanks for the candy.
You're welcome.
Shemaya, thanks for the fries.
Are you gonna